Welcome to this mini symposium. We have quite a few people in the room, and then we'll have a few online attendees. A couple of the speakers are online. So today's topic is going to be data center and power grid interactions, looking into the challenges and opportunities. So just a brief intro to basically get everybody on the same page. So we've seen a lot of growth in data center electricity consumption over the last year or two. Data center power was always growing, but it was at a modest rate, 2-3% annual growth a year in the US. And now we are talking about this 10-15% growth annually potentially. So that brings a lot of challenges in terms of the existing strain on the grid is already high. And how to build these new data centers, how to support this growth, and also while following the decarbonization and new energy generation agenda. So AI has been the main driving factor in this change. So it's important to recognize that because AI workloads are different in some ways compared to the traditional data center or cloud loads. So this estimate is already 2 years old from McKinsey, but it was basically showing gigawatts of power to be added, tens of gigawatts of power to be added, depending on the estimate you're looking at, over the next 5 to 10 years. So considering each gigawatt of power is that produced by a large nuclear power plant, you can immediately say that this is not an easy problem to have. So we can't easily add more generation, we can't easily add more transmission. So we need to find some additional solutions while we figure out how to build and expand the existing power grid for AI. The states in the US haven't seen this impact in a homogeneous way. Some states are having more of the strain. This is from the EPRI report, Electric Power Research Institute. You see that the Virginia electricity, already about 20% is going into data centers, and this is projected to grow a little further. So some states like Portland, Iowa, Texas, and they've seen a lot more growth in data centers compared to others. So many anecdotes exist on this on the internet. You can see many news articles and such, but I wanted to give a little bit of a landscape. So, of course, having this kind of data center consolidated growth also brings additional challenges to those states, to those utilities and communities. So there's been a lot of discussion lately about data center load flexibility. Tyler Norris and folks at Duke put together this report, and Tyler actually is going to be here. And I think his flight is landing around right now. So the report basically looks into what data center load flexibility, meaning, or large load flexibility more broadly, meaning like large loads basically reducing their load a few times a year when needed would bring in terms of the benefits. And it's quite astonishing. So their analysis shows that without adding new generation or transmission, today you can add 100 gigawatts of power if you provided 1% of flexibility, 1% of the time data centers reduce their power at a predetermined level for tens of hours a year. So and the number goes up, like if you provide 1%, it's actually 126 gigawatts, etc., etc. So this plot is showing how much energy can be integrated in various regions, PJM, MISO, ERCOT, and the like. So for instance, in PJM, you can get like 20 gigawatts of new data center or large loads built if you provide the flexibility. So that shows a path to support AI growth and solve this challenge that we are in. And if this challenge is not solved, like what's happening right now is that a lot of data centers are waiting 3, 5, 7 years to get interconnected because it's a complex problem, like I was mentioning, to add new generation, add new transmission in the grid. So in my team, we've been looking into data centers, data response for a while. I've done various collaborations within the EU and outside the EU on this. So broadly, what demand response refers to, and you might be familiar with this from other applications of demand response in home ACs or electrical vehicles, etc. Basically, the demand side or the power consumer regulates its power up and down depending on the grid needs. So you can visualize this as a signal, regulation signal coming to the data center, and data center can follow that within some margin of accuracy. It doesn't have to be perfect, but within some margin of accuracy. And this is beneficial for the grid because it helps balance the supply and demand. Then it's beneficial for the data center because when it does this, it can get cost benefits essentially. So we've been working on this for a while. We have a series of papers over the last 10 years. This flexibility and demand response has received a lot of attention, like I was saying, following the AI growth. So that's new. So we've been working on this for a while, and it was an interesting research problem. But now the attention is at a different level because of this energy crisis AI created. So these are some bullet points from the National Academy report from the workshop on AI-related data center electricity use. This is a workshop I helped organize with a number of esteemed folks back in November. The report is available online. So one of the things that came out, and people very frequently talk about this, is the need for collaboration and transparency to address this problem in an effective way. So how do we enable collaboration and transparency among industry, academia, governments, and communities to improve understanding and forecasting of data centers energy use due to AI? Improved data sharing and modeling was another call for action. Basically, researchers improved data sharing can be considered in two ways. One is research is dependent on having meaningful data to solve problems, but also if you think about data centers doing flexibility and demand response, that leads to this question of multiple data centers and a power grid authority exchanging information in some way. So does that work, or how does that work such that sensitive business information can be preserved? And overall, this problem is multidisciplinary because you need people from the computing side, from the power grid side, and different sides of computing. For instance, data center experts, data center power management experts, privacy experts, security experts, potentially looking into these data sharing and collaboration challenges. So that's what we started doing here. And we thought of this vision of building a collaborative framework for demand response. So in the figure, you see multiple data centers. And for now, you can consider them as part of the same region. Let's say all of them are in New England, or all of them are in PJM. And then they communicate with some power balancer, and this box of power balancer could be a centralized box somewhere, or it could be part of the power utility software. It doesn't really matter too much at this point. But basically, data centers exchange some information about their quality of service targets, whether they are meeting them or not, and they send some power bids in terms of how much power they need to maintain their quality of service. And this power balancer basically does some optimization and allocates different power targets to them. So in the first figure, I showed demand response of one data center that's following a signal. Here, each data center still follows a given signal, but the power balancer basically solves an optimization problem. So why is this interesting? Because as you build this collaborative framework, and as we've seen, in some regions, there's definitely more than one data center. There's actually tens or hundreds of data centers in some areas. So the idea is to build a framework where data centers can plug in, do their flexibility, and then everybody wins. And this requires some coordinated optimization, right? So this is what we started as a vision. But there are some challenges. So when you say, let's share some data across different data centers, etc., this is a problem. If you have looked into data center power, you can find some things, but if you approach a data center and say, yeah, I want to get all of your power data so that I can look at it and optimize it, you'll probably get an answer that's like, no. So especially from academic data centers, this is easier, but especially from industry data centers, they are very hesitant to share any data. It's more proactively protecting, like in case something bad happens. And what kinds of things could go wrong has been documented in the literature. So if you share information that opens the surface for inference of confidential information, operational data leaks, or potentially opens the surface for power-related attacks. So if you know exactly what the power consumption is for a data center, you can target their business incentives either through leaks or maliciously attacking them through various ways. So the vision then is to build this framework in a way that preserves privacy. And so we have BU, the financial privacy experts, and their folks here have designed frameworks to enable this for other applications. Basically, you can actually share information and do joint analytics without exposing this confidential information to others. And there's a variety of problems here. So can you, for instance, eliminate the trusted third party, the power balancer, using some sort of a predictive control, and many research problems follow. And without getting into specific technical details, this is what we brought us here. So we've been looking into this project over the last year. And like I said, demand response I've been working on for a longer time, but looking into this collaborative framework, how to build this right so that data centers can easily plug in, exchange limited information in a protected way, so that everybody benefits, and the grid benefits, data centers benefit, has been our focus lately. So we built this as part of a Hariri Institute focused research program, and our focused research program is called Privacy Preserving Energy Analytics for Data Centers. So our goal is to demonstrate that these large-scale data centers can achieve cost reduction and energy efficiency improvements through this novel privacy-preserving, collaborative, scalable analytics framework. So we've been looking into how to do this analytics, like what kind of analytics I need on the data center side to make this happen, how to build privacy-preserving analytics, and then also implementation of these analytics. So generally speaking, anything we do shouldn't become this new burden on top of data centers. It should be efficient and privacy-preserving on its own. So this particular focused research program, I've been working with Adam Smith and Ayse, both of whom are here in the room. Anyway. And Ayse is a computer architect and hardware expert, and Adam Smith is a privacy expert. And thank you both, and thanks to our team for working with me on this. So the program will start with 3 talks. The first one by Hendrik, Hamann. So the first talk is going to be foundation models for the grid. So this is looking into the AI and grid intersection. The second talk is from EPRI, Electric Power Research Institute, looking into the DCFlex flexibility program. And the third one is Grid-Aware AI by Vladimir Dvorkin. So we'll hear these talks, starting with Hendrik's talk in a bit. And that's going to take us till about 11:15, at which point we'll have a panel focused on exploring these data center grid intersection and the opportunities and challenges. And we have several people, Keith Menes, DOE, former DOE Office of Policy at Functions Inc., Chief Technologist at ISO New England, myself representing the data center side, and Barry Ahern, he's from National Grid. And then after that, we'll have lunch. So this is going to be today's panel. I'll introduce the panelists in more detail later. And then after lunch, and please use the lunch to discuss and make connections. But right after lunch, we'll have 2 breakouts. One of the goals in this particular mini symposium is for everybody to get something out of it. And so we'd like to have productive discussions in the afternoon, and we'll have leads for basically moderating these breakouts. To look into, one of them will look into this data sharing platform for data center energy, and the other one is going to look into data center and grid collaboration. We'd like to ideally come with next steps and action items, new collaborations, potential new solutions, maybe not solutions fleshed out completely, but the first steps into a solution. And we'll come back and discuss the outcomes here, plan for the next steps, and then adjourn. So these are going to be the breakout sessions. We'll talk about the breakout logistics when we come to that point. But that's it. So thank you all for coming today. And if you are not doing it yet, you can follow Hariri Institute from their social media links and such. So thanks to all of you who are showing up here and also online. And without further ado, I'd like to introduce Hendrik Hamann. So he's a professor and chief AI scientist at Brookhaven National Laboratory. He's also currently still IBMer, right? So I was going to say ex-IBMer, but no, still currently at IBM. So thank you so much for coming here. He's done a lot of work on foundational models for the grid optimization. So before Hendrik gives his talk, are there any questions so far? Oh, good. All right, thank you.
Yeah, thanks so much. I will talk about AI for the grid. Of course, it's a slightly different angle, although I will certainly discuss also the AI data center problem. So let's start really simple. And there's your answer. So why does anyone want to use AI for the electric grid? And I think it's pretty clear whether this is data centers, whether this is renewables, whether this is cyber security. There are many, many driving factors which increase complexity and the uncertainty of the electric grid in ways which we have not seen before. And now, of course, with this big push to growth, to data center growth, this is going to even accelerate, which means how do we want to cope with all that uncertainty, with all that complexity? Well, AI might be an option to use so we can manage, plan, and operate our grid more in a better way. Now, what kind of AI? Of course, AI has been around for quite a long time. We could go back to the 50s, but you guys remember there's early days, we did a lot of machine learning, sort of task-specific models, and deep learning came along, right? That was a breakthrough because we could discover the actual input features to these models automatically, but the models were still sort of bespoke, and now we have these foundation models. I will explain in a second why foundation models for the electric grid is actually really beneficial. But now, of course, just to summarize this, since 2017, we really have the emergence of these foundation models. So these are very generalizable, or more generalizable at least, models which you can fine-tune to different applications. So if you look on the chart from the left to the right, AI is super bespoke, task-specific, everything handcrafted. Now we have more AI as a platform, and that is also the reason, of course, why we see all this growth in AI, because we have something which is much more scalable. These foundation models, just to say, were of course enabled by massive compute, pervasive compute, really, really big data sets. And then by these two inventions or ideas, one idea is the idea of self-supervision at scale, which means you have really large training data sets that can be scaled up to really large models, and then leveraging transformer architectures, you can actually build really powerful models. I'll just explain a little bit how foundation models work before I go into the grid applications. There are 3 steps for foundation models. There is this notion of pre-training. That's actually when you build the foundation model itself. And what do? You take a corpus of data, let's say text, from Wikipedia, let's say. You mask certain parts of that data. You have an attention network, such as a transformer, and then you learn what you've masked. So in essence, you learn what you already know. And why would you do that? Well, you do that because you can teach that model that the word, for example, coffee is close to the word morning. So you start understanding, you start teaching the model how language works. You start teaching the model how to fill in the next missing token, data token word, based on the contextual information you provide. That's it. Now, a lot of the incredible breakthroughs we've seen in large language models, and they're all based on this very simple capability of being able to predict, forecast the next data token based on context. It is that simple, actually. Now, once you have that, and that is really where these foundation models come into play, why they're so beneficial, is you can relatively take that model, which has learned now the notion, let's say, of language in this particular case, and you can take it and fine-tune it, sharpen it to a particular application. So let's say you want your language model to be an expert in power systems. You feed in some power system text and literature into that model, you fine-tune it, and that can be done relatively quicker, actually much quicker than if you do this from scratch. And then, of course, the final thing, and that's actually where the majority of the energy goes in a real production foundation model, is the inference, right? You just have that fine-tuned model. It is your chatbot is being hit by different customers you serve. Now, you all know that these foundation models have taken the world by storm, right? We've all experienced it. ChatGPT is a fine-tuned foundation model. And of course, that begs the question, can we invent a foundation model for the electric grid, which is pre-trained on the electric grid data? Can we do something similar to what we have seen with the text modality? Now, when we started this whole journey of a grid foundation model, we already had some experiences with other non-text-based foundation models. For example, I've worked a lot on weather foundation models. So these are AI models for weather. And same idea, you teach a model how weather works, the physics of weather, an AI model, and then you can fine-tune it to different applications, different regions, different forecast tasks, different resolutions, etc. And in the same way, you deal with a corpus of text. Of course, there are many details. You have different weather fields. In this case, this might be matrices. You mask part of it. You teach the model how to forecast the missing or how to predict the masked tokens, and that becomes then a forecasting model. Now, what have we learned from this exercise on weather foundation models? We've learned two things. The first thing, and that wasn't just us, also many others, for example, from DeepMind, we've learned that these models actually perform quite well. So you would think an AI model might have challenges to learn the complexity of weather. Not really, it is becoming relatively competitive. The second thing we've learned is that these AI emulators, again, not surprising, are much more computationally, much more efficient. And of course, that also is not a surprise because you have this direct mapping from inputs to outputs. So we're seeing anything from 4 to 5 orders of magnitude acceleration in something which, in something like a weather forecast. So high accuracy and gigantic speedups. Now, coming back to this question, how would you now build a foundation model for the electric grid? We started this actually last year in February, and we had actually no idea how we would build it. We just felt, well, we've seen these successes in adjacent domains. We've seen the successes of LLMs. We've seen the successes of weather foundation models. So can we do anything in the electric grid? So we formed a community. Initially was relatively small, now just grown to over 280, 300 members, roughly from roughly 150 organizations. And we're still working on that, trying to figure out what is a good foundation model for the electric grid. Now, we wrote some perspective papers. We have now regular workshops and meetings on this, where we actually now also have started building these foundation models. Now, through this community effort, we ask ourselves 3 questions. So the first question was, well, given the strengths and weaknesses, or the strengths of foundation models, how would that map to something in power systems? So what are the strengths of foundation models? Well, I already explained, right? They're really good in next data or next token prediction based on context. Of course, we have tons of forecasting challenges in the power grid, right? Load forecasting, but also power flow, state estimation. So a bunch of use cases lend themselves to that particular salient feature of foundation models. The next is they can be adapted quite well. Does it actually make sense to have a foundation model which can be adapted to different applications in power systems? Well, if you think about it, in the United States, we have roughly 2,000 different utilities. They operate different grids. So if I could have one foundation and then fine-tune it to these different grids and grid applications and requirements, that might be really beneficial. And then finally, this massive acceleration which we see with foundation models compared to physics-based simulations. So that's what we learned from the weather story. Well, there are many examples, I think, where acceleration can really help with grid management and planning, right? So, for example, you think about simulations of both distribution and transmission. You think about N-2 contingency analysis or something like that, or even accelerated interconnection studies. The next question we ask is, what knowledge? So let's think about it, right? We have LLMs that capture the knowledge of language. The weather foundation models, they capture the physics of weather. So what would we actually capture in the grid foundation model? And then the final question we ask is it actually feasible to build? Right? A lot of people say, oh, there's no data, you can't build it, right? So forget about it. So we came up with an answer to that, and we are pursuing that path. And it's actually a relatively simple answer. We decided to start with a foundation model which we pre-train on power flow data. And most people I tell this, they say, well, power flow, they're not really excited about it. And I think the reason why they're not excited about it is because they don't understand that an AI model for power flow is fundamentally completely different than what we have today when we solve the Newton solver equations. So how do we do this? We represent the grid, right, as a graph, as you would. You have the edges, which are transmission-based. You have the transformers, you have load buses, generation buses, you have a slack. You have your different values, same way you did it with the text, or same way you did it in the weather domain. You mask part of the information. We teach the model to learn to reconstruct the missing values. That is the foundation, right? Okay. Now, where do we get the data from? Okay, so we said let's start with the really boring stuff, the synthetic grids, right? So there's a whole set of course, synthetic grids which are available. They are, of course, all the IEEE test cases. There is a lot of really good work done funded by EPRI, of course, on synthetic grids done by Adam Durchfield out of Texas A&M. And so we started with these grids. Now, how do we generate now these data sets? We have over 50 different grids. We need loads. So where do we get the loads from? Well, we decompose aggregated loads from these different grids. We have then disturbances to these different grids, so we can teach that model a broader range of load conditions. Then we have different topology perturbations which we apply. So we run, for example, contingencies. We solve power flow, optimal power flow over and over again to create these training data sets. That's what we do. The goal is to build an emulator. That's really what it is, right? And build a full data pipelines, many different grids, many different topologies, many different load profiles, and then hope that that model learns the physics of power flow. Now, once we have all this data, we need to pre-train. I told you there's 3 steps. So this is when you build the foundation model. Of course, you're going to normalize this data. You do the masking. We use transformer, graph neural net. We have a physics-informed loss function, which helps us with the training, and that's how we build our foundation model. Pretty simple. How does it look? So that's just an example, super simple grid, right? On the left side, you see what a numerical solver would give you. This is the active power demand on the different nodes. This is what we mask, and then we ask our grid FM to reconstruct, basically predict all the missing values. And this is just a graphical, it's just a visualization you can see, but you can see this model is actually predicting quite well. Okay, so now we have, and this is actually some early experiments. So now we have an idea how to build a grid foundation model. So we said very early on, let's take 5 different grids. These are little tiny toy grids. And let's see if we pre-train a foundation model on these little grids and we go to a much larger grid, do we see any benefits from having a foundation model which we pre-trained on these smaller grids? So we did this experiment, and you see here on the left side a pre-trained foundation model which you've trained on completely different grids, helps with the fine-tuning to a particular larger grid. You see faster convergence, you see better accuracy. So you can see that this idea of building a foundation there's some evidence that this actually can work. On the right side, you see, if you fine-tune now this model, the pre-trained model, you need less data. So that's also very good, because that would allow an utility, for example, or a customer to build a more accurate AI model with less data because we did the pre-train. Now, the one thing I also want to point out, when we started this whole work, a lot of people said to me, this will never work because you got to pre-train or fine-tune each time you have a different grid. But that's not true, because we're having all these disturbances for a given grid. We can go all the way up to, let's say you have a 300 case, all the way up to, let's say, a contingency of -5 or 6, and the model will just perform because it has seen all these different cases. So it's all done in the fine-tuning plan. Now, is it really faster? So that was, of course, this first question. This is data from a 300 node grid. So it's a smaller grid. It actually looks better if you go to larger grids, but you can see here that, so we have plotted here on the y-axis, basically the error, which is the residual in the active power. On the right, on the x-axis, you have the compute time, but you can see that the grid foundation model is actually much faster, 50 to 1,000 times faster. It's actually much more accurate than the DC power flow, and it is not quite as accurate as the AC power flow with the traditional solvers. Okay. Now let's go to some real use cases. Some people might say this is not a real use case, but the use case I personally was interested in saying, how can we do N-2 contingency analysis? Now we have a faster solver, can we actually do that? And can we get actually comparable results, or even better results in terms of the accuracy, but faster, as we compare them to AC or DC power flow solver. So what we've done here, we've taken the 300 node grid. If you look into N-2 contingencies, these are 80,000 contingencies. So if you just run it for one load scenario, you would have to run 80,000 contingencies, and then of course for every 5 minutes, whatever your time interval is for the 24 hours. Now that becomes impractical for larger grids. So now we are running this model in N-2, and we're looking into the contingency by relations. So note now the metrics we're evaluating this model is not anymore just the difference to an AC power flow solver, but it is actually the classification. So there's a classification insight. And what you can see here is that you can get with such an AI model all the way to N-2 contingencies in a fraction of the time, pretty much the same performances. Okay, so how can that now help with the whole data center issue? So here's one use case we have been looking into, and it is arguably quite naive, but I think still quite interesting to look into. So, think about it. The Texas transmission grid. This is, of course, not the real Texas transmission grid. This is actually synthetic grid of the Texas transmission grid, which you see there. And there's a version with 2,000 nodes. In that version, you have roughly 1,100 load nodes. So the question you could be asking is, what is the best place to connect 100 megawatt data center, right, across all these 1,000 nodes? And how would you figure this out? Well, you would run all 4,000 contingencies, and you might want to do this for 10 different load scenarios, let's say 24-hour load scenarios, at 5 minutes intervals. That means to figure out what is the best place to figure out all the contingency violations for that grid, for all the 1,100 node connections you could possibly have there, you would have to run 10 million more of those connections. That would take a long time, but now we have something which is 100 times faster. So the idea here is, and we did this for one case, is why don't I pre-screen the grid, assuming my data center can be anywhere. Most data centers can be anywhere. And I pre-screen and figure out all the load buses where I have the least amount of contingency violations once I connected 100 megawatt load to it. And you can see here, this is the numbers of contingency violations. Some have 20, some load buses, and these are the numbers on the y-axis of potential load buses you can connect your 100 megawatt load in this particular case. And what you can see is, yeah, there are places, of course, where you can connect much more easy and much easier than other places. So it's an example how we can help potentially with the connection problem by pre-screening, and not what today the industry is doing. What I've seen is they basically apply in 2 or 3 locations, then they apply for the interconnection process, which then takes them whatever 3, 4, 5 years, and then they're being told, oh, you gotta build a new substation or whatever. Okay. So where are we going now with this grid effect? And I said earlier to you that a lot of people aren't really excited when I say, oh, we're having now an AI emulator for power flow. I tell you, the reason why we chose power flow is because we can actually extend this foundation model, hopefully we can prove that, so we can actually address many more applications. So currently what we're doing is we're basically just masking the individual values at the different buses. And so I call that bus value reconstruction. That is a pre-training task. Because of that, we can do load flow, optimal power flow, we can do some state estimation, we can do contingency analysis, etc. So these are the applications, so power flow-centric applications. But of course, I can also have multiple load. I have my load profiles, so I can also ask my model to predict the next power flow values at the different node buses. So that will open, once I add this pre-training task, it will open up other applications such as load forecasting, renewable energy forecasting, looking at power flow, etc. And of course, planning stability analysis, although we need to create different data pipelines if we want to do that. And then the final thing is, who says that I can't just also learn the edges? Right? I can have my model training to predict the different edges, the transformers, the transmission lines, etc. And so once I get into that, I could think about control operations, much more automated expansion planning, and so on and so forth. And with that, I just want to show you where we're going. We have a relatively simple foundation model built as we speak. You can see that here on the chart, right? How things have progressed. We have a relatively small model. So we're not really adding, by the way, to the energy consumption, the data centers, at least as of now. Of course, we have plans to build more scenarios, build larger models, so to get better accuracy. We have ideas of the pre-training to extend the use cases, right? Not just the bus planning reconstruction, the timing reconstruction, and then also the edge reconstruction. And we have a whole pipeline that is all done to the community of different data sets which we're generating to have more diverse pre-training. And of course, we're extending the cases. With that,
yeah. So we have this microphone. I think we need to use them for questions. Thank you.
Hello? Okay.
sorry.
So I'll just kick off with a question. For those who are a little late, Hendrik has been doing a part of this AI for grid space. He's at the Brookhaven National Right, also Professor at Stony Brook. He was a former chief science officer at IBM. It's still at IBM, so just a late teacher point, not show up. So my question is kind of related. You mentioned the lack of data that kind of guided you into power flow initially. So what is the lack of data in the grid space? Like, what is the data challenge? And connected to that, can utilities, ISOs, and the like use this kind of model for their own data? Like, would there be an interface? Like, I have my own data, and I'd like to provide that data to the model that you have and kind of like fix this customized model for myself.
Yeah. So maybe I answer the second question first. So that's the whole reason why I think foundation models are really good, because you can build a foundation, and you can do that with synthetic data, with open data, or maybe at some point we can also contribute together to build that foundation. Privacy issues, of course, as you know, potentially. But then once we have that, everyone is better off. That's really also the reason why this community which we build is at least growing, because we build that foundation and then you take that model behind the firewall, and it allows you to build a much better model than without it, right? And just with your own data. So my vision with this foundation model is that it's in the open source. It's an open source model, and anyone who wants to use it can take it behind the firewall to do a lot, what they like to do, and fine-tune it. And so the idea of this fine-tuning, the fact that you need less data for fine-tuning is important. Now, in our case, the data challenge, the main data challenge we have, even with the powerful, is, of course, we wish we would have more synthetic weights. We don't need to read weights for a foundation model, more realistic weights, but probably most importantly, we don't really have good load profiles, I would say. That's probably one of the areas which is somewhat challenging to find really good load profiles, because at the end you want to train your model based on representative load profiles, and if you don't have them, then that's very difficult. As you know, right, the ISOs, they are publishing aggregated load profiles. But of course, we need to know what are the load profiles in the bus. So we're trying to de-aggregate that, which is really painful. So basically trying to figure out, okay, I have the aggregated load profiles of, let's say, 100 load buses. I have some idea about the residential, about this, about that, right, about the weather and whatnot. Then I try to de-aggregate it and then bring it down back to modern statistics. So far we really don't have really good load profiles. So,
That was another question.
We see the commercially and it's very interesting presentation. I'm very interested in the knowledge provided here and the interaction we're going with the parts information model. Follow up the question, previous question, you talked about the model. If I understand correctly, we were talking about having a small set of system, and you're using actually 17 buses and 39 buses to 200 buses. So if you can generate all type of scenarios and you train model, that's called foundation model. And I assume you're kind of defaulting that model where you check on the critical, right? So to have that data, it's all options than the data. And then you were saying, I think you mentioned that once you build a foundation model, and then you can adapt to different systems, right? So you're saying, okay, for example, actually you have already used it. I'm gonna just fine tune the model. It's our input. So that's why I'm not very clear when you say that, we still lack with data. Is that gonna be part?
yeah, so makes sense.
Data being that for practical usage, you lack with data, or you say foundation model itself, you lack with data.
Yeah, so the one thing, remember, okay, the one thing we have done is, and we have really good results, is, let's go back here. We have a foundation model which is really good in predicting the missing values. It's basically a power field foundation model. right? Works great. Now, the next step we want to do is we also want to have predictive capabilities of that model, right? I know today when you run your power flow, your Tara, whatever it has no predictive capabilities, but there is no reason if I would have realistic load profiles that I could not build a foundation model to predict the next value at all these different nodes based on the contextual information which I have. And so for that, I would need realistic load profiles. So that was really my comment. And so you're right. You can use that today. Great. In fact, there's going to be a starter kit now. So this model also going to be released in open source as a Linux Foundation for Energy project. But of course, we want to also try to address some of these spaces.
So quick question, Lexi. Thanks from Hariri.
So yeah, excellent presentation. Very national grid. So as you yield any macro output from your analysis, you're caveating things as they get in the way of fidelity of what you're saying. So I guess one thing that pops up frequently as we study things is generation assumptions. So if the output say is great foundation model, which again is great, we thought would be that location X would be an ideal place to put 100 megawatts of power. You would caveat saying it doesn't look into the availability of gas, water, it doesn't look into also all the physical parts, but on the actual study piece, when it work, do the assumptions made about generation, could that, I guess, yeah, how firm are you with your belief that the system robustly addresses the generation factors in this assessment, or is that something to look further into?
I think to the second part of your question, certainly something we still need to look into more. Remember, this is a relatively new work, right? So kind of, so it's early work. Something we need to work on. That's why we have this community, so we can actually figure this out together. Where are some of these limitations? So I also want to say, completely appreciated that the data center location. Of course, you need fiber, you need the land. There's all these other dimensions. Now, this is only a piece of it to figure this out, but it could be a really useful pointer to say, why don't I look at these locations first? Because I know my infrastructure upgrade cost is most likely to be less, because I can do that. I can do this calculate this in a day, for example.
Completely great.
Great. So last question from Keith, and then we'll go on to the next one.
Okay.
It's a button.
Hit the button. I think that. Yeah. And now everything.
There we go.
On the data, data question, what's the obstacle to getting that? Yes. Like I think there are 3 or 4 categories. One's privacy concerns, and safe harbor. Commercial concerns, one is security concerns, particularly infrastructure. One is just things that won't change regardless. Okay, which got that stuff.
Yeah. So really good question. My sense is, of course, for good reasons, utilities, ISOs are over careful. Of course, there are rules about this. But if there's any, any way they can even oversight on not sharing, they would always do that. Right? I see a lot of really good work. For example, in the EU, right, they have a lot of open grid data initiatives. We had EPRI, they pioneered these synthetic grids, that's a great one. So maybe there are other ways we can actually think about this and collaborate in building really data sets which can actually do this. And that would be super helpful for this question as well.
Sure.
Right?
Thank you. So the next speaker is going to be Anuja Ratnayake from EPRI, Electric Power Research Institute, and she's going to talk about the DCFlex initiative. That's about data center flexibility.
Well, thank you so much for having me. My name is Anuja Ratnayake. I'm part of the EPRI team. I have the responsibility for the DCFlex initiative, which is what I'll touch on mostly today. So my focus today will be more from the powering the data center growth and the AI evolution perspective, and less from the building AI as a solution for many of the challenges the energy industry has perspective so much. With that, let me set the context very briefly. I have two slides here that is literally telling you what does growth look like from a energy point of view. You can see in this first slide historical growth, which was primarily driven by the mass market or the average consumption from households point of view. But when we look to the future, the growth rates look very similar. The big difference post 2025 from a trends perspective is, instead of this growth coming across many endpoints, it's coming from a handful of sectors. And some of these sectors are very large single point loads. So my way of thinking of this is, up to now, we've seen smooth peanut butter in our growth. Looking forward, what you're seeing is more of a chunkier version of it, and the chunkier version brings new types of challenges the industry has to rise up to. This next slide shows you what the chunkier pieces are. And as you can see, the orange-yellow color here is data centers. The all of the sources for what you see here, the conference coordinator, so you can dig deeper and understand the growth assumptions and why you see this picture. But really, the intent of my using these first two slides was to ground you on what it is that is coming at the energy industry, that as an industry we need to rise up to. The most important piece from this slide that I want you to have in the back of your mind is this idea of clustered growth. So the scale of growth is substantial from data centers, but this clustering creates an additional challenge for where the data centers are anticipated. What this means when you look at this future is, it really means there is opportunity for collaborative development across multiple areas. From the energy utility point of view, there is a evolving need for thinking of the planning discipline for utilities with a little bit more creativity and rigor. There is a need to rethink how load interconnection is done. And then there is the need for balancing the pace of infrastructure availability to the bill impacts for the average society at large. With this in the back of our mind, I'm going to shift to the DCFlex initiative. As I mentioned, DCFlex is my primary focus within EPRI. DCFlex is trying to address one specific problem. I shouldn't call it a problem. One specific challenge that's coming at us from this data center growth. And that sits in the timing. So from the data center point of view, data centers look at the need for energy to address particularly the AI growth they are seeing. And they're looking at the need for that energy in a 2 to 3 year window. So what we see from coming from the data center industry point of view is, within the next 2 to 3 years, there is an expectation for larger and larger data centers compared to what we've seen before. What that means in numbers is, what we've seen as data center size over the last 20 years is anywhere in the range of 5 to 100 megawatts range. What we are seeing in interconnection queues, when you look at the next 2 to 5, 10 years forward, is in the range of 500 megawatts to multiple gigawatt scale. but the data center industry is looking at that growth and going, I need to be up and running in a 2 to 3 year window to be operational for this new data centers that I need in place. From a electric utility point of view, the industry needs a substantially longer time period whenever it's a 500 megawatt or larger single point load that they have to serve. And that need for a longer time period comes from having to build new transmission assets and having to build new generation assets to serve this significantly large load. Normally, that is a 7 to 10 plus year time horizon from the utility industry. So this mismatch between data center expectations of wanting to be up and running in 2 to 3 years against the utilities' traditional capability to interconnect a load of this scale being in the 7 to 10 plus years, that mismatch of timing is what DCFlex was targeting as a challenge to solve, right? And the only way we could see to solve that is by creating the load to be flexible load. What we mean by flexible load here is a load that no longer requires 5 nines reliability with a 24/7 fairly static profile. If a data center could go from that traditional 24/7 flatline load profile with 5 nines reliability requirements that they generally ask for in an interconnection request to being more flexible and responding to grid needs, and therefore creating data centers that are grid resources, now we can talk about meeting the 2 to 3 year time horizon that data centers want to be interconnected at. That was the grounding point for DCFlex. And the way we were thinking of it is we need to first identify whether flexibility exists in data centers to rise to being a flexible load. And if it does exist, then how can the utility industry embrace that flexibility, make it part of their operational day-to-day, make it part of the way we plan for the future. That was the rationale behind this entire exercise. So you see 4 work streams identified on the right-hand bottom of this page. This is how we were going about structuring our work. Workstream 1 is focused on what kind of flexibility exists in data centers and how can we create a reference architecture that data centers can then leverage as they think about becoming a flexible grid asset. This includes a large portion of getting the data center designers and operators to understand the complexity of the utility grid, what it means to be a grid asset, and then creating a set of design criteria that says if you are able to adopt and address XYZ, you can become a valuable grid asset. I'll speak here briefly to what it is that we'll be addressing as part of the data center flexibility capabilities. We put this in 3 buckets. So traditionally, if you think of demand response programs in the utility sector, the demand response programs have been mostly focused on the major working load inside a customer's premise. In the case of data centers, this is the server racks that does the actual computing piece. One piece of the flexibility that does exist is that computing energy consumption and whether there is flexibility within the computing itself. The second big piece for data centers is their auxiliary power, particularly their cooling power, tend to have some flexibility elements as well. Figuring out how much depth still exists in the auxiliary power piece is the second piece of solving the puzzle for flexibility. The third piece, we as the utility industry have not necessarily considered within our demand response in a traditional way. This is the backup generation piece. The vast majority of data centers that exist today have some sort of backup. Most of that backup tend to be from tier 2 diesel solutions. tier 2 diesel engines cannot operate when the grid is up. So this traditional form of backup generation cannot enable the data centers to be a grid resource, a flexible grid resource. But if we are able to swap out the tier 2 diesel to be either a different fuel using the same gensets, or completely rethink the gensets itself with alternative technology solutions, now that creates the third leg of flexibility for a data center customer. These are the three legs of the stool that we are touching when we are looking at workstream 1 and trying to address how can a data center by design be flexible. Within workstream 2, we are looking at this from the other side of the same coin. So workstream 1 looks at it from the data center point of view. Workstream 2 looks at it from the utility program side of view to say, if I had large loads that had flexibility in this manner, what kind of programs would enable them to actively participate in grid needs and create a collaborative environment where their value is properly captured by the larger societal interactions. The transformational utility programs workstream is looking at this both from the retail tariff point of view, but also from market programs point of view. Then workstream 3 looks at this from a long-term planning point of view. This is where utilities need to recognize large loads that have flexibility in a more comprehensive way than we've necessarily done up to this point. What I mean by comprehensively is we've looked at load flexibility as either a net load reduction in our planning or as a peak only contribution. But what we see the full flexibility capability of a data center where you have these three types of flexibility, it needs to be represented more as a dispatchable asset in the planning world. To capture the most value from a planning point of view. And getting that right is part of what workstream 3 is going after. It's getting that right and then addressing the interconnection side challenges, addressing things like how to be transparent in hosting capacity, how to enable better conversations between data centers and utilities at the very front end when they're both in the planning stages. That's the kind of thing that we're addressing in workstream 3. And then in workstream 4, we are looking at this more holistically, understanding the profile of new AI data centers in particular. It is no longer a flat line energy consumption pattern that these large data centers will be representing. What that means is we have to figure out the right mix of generation solutions the utility need to carry in order to serve the data centers. This is the piece that we're trying to address with workstream 4. So at a very high level, this is what DCFlex is. The point that we are trying to get through here is understanding whether data centers actually have flexibility and then applying the understanding of what that flexibility looks like within the utility community so it gets captured and valued appropriately for the benefit of the larger society. As part of DCFlex, one of the things we are doing is demonstrations. So the intent with these demonstrations is to be with live data centers in the field that are operational data centers, work with them to confirm the depth of the flexibility they do have available, and then working with them to test and validate the type of program frameworks, the type of operational tools we are coming up with as part of DCFlex can be adopted immediately and creates the right impact. Our plan is to have approximately 10 plus demonstration sites. We've identified the first few in that list already. I cannot communicate that just yet, but some of that actually addresses this primary workload flexibility, the compute flexibility, and that's been incredibly exciting for the work we are doing here. I'm going to very briefly show you the current mix of partners we have coming together for DCFlex. I'm actually going to leave this up on the screen, and because I'm really short on time here, maybe I can open the conversation for any questions.
You can speak right now. Can you hear us right now?
Yes, I can hear you.
So we'll tell Fatin and he'll say. Any questions? Apologize for the technical breakdown, but let's get a question.
Just a quick question about the tier 2 diesel generators and the fact they can't operate when the grid is up. Is that a technological issue with the generators, or is that about air emissions permits? That does a lot of that.
Yes, it's related to air emissions. So the air emissions for tier 2 diesels essentially limit at a federal level, it limits the ability for tier 2 diesels to operate. It's essentially limited to 50 hours a year and only during emergency conditions, which is defined as when the grid is down. So in other words, when the grid sends a signal that says, I'm expecting to be down, if I don't have resource help, please reduce your consumption. The large load owner cannot operate their tier 2 diesels to support that kind of a request. That's the recent tier 2 diesels cannot be supportive as a flexible element right now.
Yeah, I have a question. So it's I think the chart actually shows it quite nicely, right? It's a relatively complex supply chain, right? Because you have companies who are providing data center space, then you have equipment providers, you have people who are writing the middleware, which might be able to manage it. You have, you have then the cloud providers, let's say, and then they have customers. So how do you envision that all come together, right? It seems like, it's such a complex supply chain. So it's not really clear who you want to talk to. I understand you're trying to talk to many, but I can probably also see many folks who are probably not on the chart, right? Which are also part of this complex supply chain. And so, yeah, I wonder your thoughts on it, how you guys think about that.
You're absolutely right. Even though we call the data center industry a single industry, the ultimate customer for the utility, the ultimate customer, the data center is not a single flavor. So we have the new large AI data centers, and majority of the conversation we are having is related to the new AI data centers, but there is a recognition when we look 5-10 years down the into the future, there's still going to be cloud service providers. There's still going to be some amount of enterprise data centers. The idea here was to try and figure out how do we come up with a set of guidelines that would address about 80% of that total market. We're not going for the 100%. So for example, crypto mining, we are not focusing heavily on crypto mining data centers because what history has shown us is crypto mining is one of the most flexible loads. If you look at the data sets coming out of ERCOT, you'll see that there is crypto mining data centers that are responding to market signals now in such a way that it is sort of the perfect flexible load. So we are not necessarily focusing on business models that have the flexibility inherently available, and crypto mining seems to be doing this primarily with their workload itself and not necessarily depending on their cooling loads, etc. So we are focusing on, like I said, 80% of the mix instead of the 100% of the mix. But the other side of it is, even for that 80%, we are not going with blinders on to say everyone's going to be a AI foundation model or a training module data center, and therefore they have inherent flexibility capability. Instead, we are in our work stream 1, where that reference architecture deliverable exists, we are looking at it from how do you create ability to rise to this flexibility need by moving the 3 legs of the stool around. So, for example, a cloud services data center may not inherently have huge depth when it comes to their compute flexibility. But understanding that enables them to create the backup solution and potentially the auxiliary components to be more flexible than, say, an AI data center that seems to, at least at this point in time, have more inherent depth in their compute flexibility. Hopefully, I'm answering your question. I think the big message I want you to take in this answer is we are not thinking of it as one model will fit every type of data center. We are leveraging the 3 legs of flexibility available inside a data center customer to come up with how to create the right model depending on the type of workload carried by the data center and the type of ownership for the data centers. So, for example, colos might not have the same level of flexibility capability as, say, a hyperscaler who owns their own. And understanding that and providing sort of a model that both sets of ownership can leverage, that's part of the mix of deliverables for Workstream 1. Did I answer that question adequately? It might be something that is worth doing a deep dive separately if that's more desirable.
Thank you, Anuja. And thanks for waiting patiently as we went through the technical difficulties. Thanks a lot for joining. So we'll move to the next talk. I hope to catch up soon. Thank you very much. He is working at the intersection of power grid optimization as well as some privacy challenges of power grid optimization. So he is going to talk about his work briefly today. Vladimir, when you are ready, please feel free to go ahead.
All right. Yeah, let me get started. Indeed. Yeah, thank you, Ayse, for introduction and for accommodating me online today. So it's great to join you for this workshop. So I'd like to start my talk talking about what makes data centers such a special load. So data centers present a big challenge for electric power grids because of their disruptive electricity consumption. So here, what you can see on this picture on the left is a simple random draw from the MIT SuperCloud dataset, showing how a large language model consumes electricity over time. And what you can see that it presents sharp changes in electricity consumption. It can go from almost 0 to 200 watts in a matter of seconds and then go back. And these patterns are very hardly predictable. So including these electricity loads in electric power grid presents big operational challenges. As much as challenges that they have, they also present a lot of opportunities to help electric power grids to operate better. So here on this picture, you see New York ISO system and 5 installed data centers. And specific flexibility feature of data centers is the ability to spatially shift the workloads from one data center to another. How it can help New York ISO is to move workloads from the south of the state during peak hours to the western, central, and northern parts of the state, and thus help the grid to operate at a better, cheaper cost. These new emerging AI loads also provide a lot of opportunities for demand engineering. the training of large language models can be optimized to reduce the peak power reduction with a minimum to none impact on performance. And this also provides important opportunities for electric power grids to operate better. And talking about grid integration of data centers, so I would like to first show you the timeline of decision making in power systems. So decisions in power systems starts far ahead of real-time operations, years ahead when we decide on optimal grid design and expansion decisions for transmission generation. If data centers enter conversations with power grid operators at this stage, there is a huge potential benefits from coordination that can be measured by gigawatts of power coordination. There is decisions that needs to be done months, week, or day ahead of operations. So these decisions concerned optimal load forecasting, some preliminary dispatch decisions, or maybe generator maintenance. There is significant potential to coordinate gigawatts and megawatts of electricity demand coming from data centers. More short-term decisions at the ahead stage. That's where grid operators clear electricity market, and data centers, if participated in the electricity market directly, can coordinate gigawatts and megawatts of power with system operators through market mechanisms. And there is also a lot of potential to coordinate megawatts of electricity consumption at hours and minutes before operations. And there is some small potentials that are still left during real-time operations, seconds ahead of operations in a timescale automatic generator control in high voltage grids, and maybe similar control timeline in distribution grids. And the sooner you start the conversation, the better. So in today's talk, I want to talk about coordination with of data centers with electric power grids at the day ahead operations, hour, minute ahead of operations, and a bit of a week ahead operations too. So I will overview some pieces of our work, starting with hierarchical optimization models for coordinating spatial data center flexibility with power grids. I will then talk about how similar coordination benefits can be delivered by existing market mechanisms. And time permitting, I will also talk about distribution level energy storage solutions to smooth data center loads. So I will start with hierarchical optimization, and this concerns like day ahead operational planning and hour minute ahead operational routine in high voltage grids. Think of electric power systems as a graph with a set of edges, transmission lines, and nodes, electric power buses. And in every bus, there can be a source of power generation and electricity demand. So the classic optimization problem solved by grid operators is to take this representation of the graph, solve an optimization problem. You'd like to find the optimal dispatch decisions P for every generator across the network to minimize the total dispatch cost while ensuring feasibility of grid operations. And that means that every generator operates within the limits, conservation of power flows, and meeting other grid limits. And this is a standard problem solved by system operators on a daily basis. But now there's new players in the game, data centers, that have their own optimization problem. So these data centers here are depicted in the blocks, blue blocks. So they have their own network, usually users of data centers that submit their jobs, workloads to data centers. So data center operator would like to take all these computing demands and allocate them within the network of data centers. So one very typical performance metrics here is a latency. How long does it take to get the job submitted and respond back with an answer? So data centers would like to allocate these jobs by minimizing the latency across this communication graph, subject to constraints that all the computational demands must be allocated. We cannot overcommit data centers with respect to their limits, computational limits, so on and so forth. These two problems are typically completely separated. So what we like to do, we like to formulate some instance of an optimization problem that can co-optimize this process, right? The problem here, we just cannot adapt the two objectives and constraints and solve one optimization. Rather, we want to formulate hierarchical optimization problem that will respect the timeline and decision-making of two operators, grid operators and data center operators, and solve this problem jointly. So, yeah, just before formulating it, last point is to say that the unique feature of these data centers is that they form the virtual network where the workloads can be shifted from one data center to another in a matter of a few seconds. And this variable phi is a coordination variable that moving the loads from one data center to another, data centers can help the grid. So to find these optimal task shifts, yeah, we do formulate this hierarchical optimization problem. Here, you recognize the problem of a data center power grid operator that minimizes the cost of dispatch, and it additionally optimizes the optimal task shift, shifting the loads from one data center to another with respect to nominal schedule of data centers. This coordination variable enters the feasible space of the network of data centers, and they respond with the new optimal electricity demand. Solving this hierarchical optimization problem, where data centers optimization is embedded as a constraint into grid optimization, solving it in a closed loop, we can find the optimal task shift. So the optimal task shift is the one that minimizes the dispatch cost in the power grid, but at the same time, it respects the objective and constraints of power grid and data center operators. The challenge here to solve this problem is very difficult in real time. So we need some real-time online solutions, how we can approximately solve this problem throughout the day. And the solution that we come up with is using contextual regression to approximate the solution of this hierarchical optimization problem. So to contextualize this process, so consider features that are specific to every coordination scenarios. These features can be nodal prices, loads, generation statistics, so on and so forth. And the idea is to train the optimal coordination policy that will take this current operation condition, prices, loads, statistics, and map them into optimal task shifts across the network of data centers. So it can take the form of this regression that we like to train. The question is, where do you take all these contextual features from? They're all available from a real-time dashboards of system operators of New York ISO, New England ISO, and this information is also gathered in the modern Greek analytic startups like Grid Status IO. So now, having abundance of this data, what we like to do, we like to train this policy, so we don't need to solve optimization, hierarchical optimization online. Instead, we will just map the operational features X into the optimal task shifts of NetDC. So this is a classic machine learning task. So here you have our features X, they map using regression weights beta into optimal task shifts, and all these weights, regression weights, they are same for all coordination scenarios Q. And we also can use some means of L1 regularization to get only best features that help us to map the contextual information into task shifts. But solving it as a classic ML problem using empirical risk minimization brings a lot of disadvantages, including the constraint violation. So to ensure that this policy and this regression, contextual regression, respects grid and data center constraints, so we use the same hierarchical optimization that I introduced before, with the difference that it's now solved for the policy and across many coordination scenarios. So here, grid operator would like to minimize the average dispatch cost across many Q number of scenarios, subject to power grid constraints and subject to constraints on task shifts that now they're restricted to this affine policy of the function of the features. This task shifts will enter Q number of embedded data center optimization problems that would minimize latency across Q scenarios and stuff like that. They will respond with the optimal demand in every scenario. And the optimal solution to this problem gets us the policy that minimizes the average grid cost, but also respects grid constraints and constraints of data centers. Just to give you an example how it can work for New York ISO. So you have this 11 zone representation New York ISO. You have 5 data centers installed in this network. And we like to see how this coordination looks in action. So this example here of ideal coordination when data centers and grid operators bring all data together and solve hierarchical optimization problem to get the optimal task shift. This is ideal scenario, but it's important to use it as a benchmark. So you see that there is a natural logic to it. You like to move the loads from the south of the state to the western, central, and northern parts of the state to offload a very loaded area of New York City. By doing these task shifts, you can significantly reduce the operation cost or unit commitment cost in the power grid. Here you see these lines, the operating cost of a power grid, and this green shaded area, this is a time of coordination during peak hours. Invoking this special flexibility of data centers, we can significantly shape the peak and also substantially reduce it depending on how much flexibility data centers are willing to offer to power grid. Starting from almost zero flexibility there is, in terms of latency, there is still some potential to save the cost. Increasing the latency loss, they can provide more flexibility, thus reducing the cost more significantly, but there is a diminishing effect of it. And this a diminishing return on DC flexibility is due to hard unit commitment constraints at New York ISO. Anyways, here you have 5 locations where data centers are placed. The red lines show the baseline loading of a data centers, and the green bars show you the allocation of electricity demands across data centers after special task shifts. And what you can see is that for 6 p.m. hour, this is a peak hour, New York City is unloaded as much as possible. And all this space here, empty space here between the baseline consumption and the green bars is actually moved to other parts of the state, to central, western, and northern part. And the solution is quite logical and adheres to some rationale, right? The problem is that getting the solution by means of optimization is very difficult. Privacy constraints, restrictions on data exchange, and also computational capacity. So here, the blue lines here show you how we can approximate this ideal optimization-based solution with a contextual regression. And you can see that the numbers are very similar, right? When we train the coordination policy on the features like zonal demands in New York ISO, electricity prices, renewable power generation, and the power flows between these aggregated zones. So the coordination benefits are huge. Here you can see what is the cost of New York ISO dispatch in a peak hour as a function of different penetration level of data centers. So the green bar shows you the best ideal solution we like to attain. The gray bars shows you the solution when no coordination is taking place. Everyone is ignorant of the problem of increasing costs thanks to data centers' growing demand. And the blue bar here shows you like this contextual regression. The red line shows you regression solution following standard machine learning routines, no grid feasibility, no data center feasibility. So it's not the best policy. So what you can see is that this contextual informed regression is very good in approximating the ideal coordination, especially with respect to the non-coordinated solution. What is also important is that you see as data centers penetrate the grid, the cost increase using quadratic function, right? There is a quadratic increase in cost. But if you start this coordination with data centers and you use this geospatial flexibility, you really see somewhat linear increase in cost, which is obvious benefit of coordinating with data centers. It's also important to think of what are the optimal features that enable this coordination. So we can use all the features from dashboards, or we can use only 3. Apparently, there is a lot of room in selecting these features, and we can do it with L1 regularization as a part of that hierarchical optimization of the control policy. You see that you can use up to 29 features. It can be different electricity demands, power flows, zonal electricity prices, right? As you start more heavily regularize your policy, you sort of give up some features while attaining more or less the same amount of coordination benefits. And what is interesting is that you can run the whole policy of moving the loads across the whole in New York ISO by using only one feature available from a dashboard, and that feature is the most important demand in New York ISO is a peak electricity demand in New York City. So just whole load shifts in the whole New York ISO can be pre-computed by our policy using just a single feature. All right, so there are a lot of benefits from coordinating data centers and power grids explicitly, but can we achieve this coordination implicitly using existing market mechanisms? And next part of the talk, I will talk about electricity markets and how they can incentivize data centers to invoke special DC flexibility. Before that, I need to briefly explain how electricity markets work. So electricity market in a nutshell, or in a very simplistic setup, works by solving so-called optimal power flow problem. So system operators like to find the least cost generator dispatch, P, that will meet all the demands in the network, right, at the least cost. So they would minimize generation costs subject to power balance constraint and power flow limits. So this problem is solved on a daily basis, and the dual solution to this problem gets us electricity prices, LMPs, that are used to price electricity. So they're specific for every node. They have some uniform price component, and then which is adjusted to respect the congestion in the grid. And what is interesting, when we look at the duality theory, we can see that the optimal dispatch cost here, the objective function of this problem, is proportional to the demand charge. D is a demand of data centers. P is a price of data centers demand as a function of data centers demand. And this component is proportional to the cost, meaning that if data centers will try to minimize this charge, then they will implicitly help the system to minimize the cost of electricity. And you can see this effect on this map. This is standard IEEE bus system. You red dots here shows you the locations of 10 data centers, and you see that there are expensive nodes in the system, there are less expensive nodes in the system. Moving workloads from these expensive parts to the less expensive parts, data centers save a lot on electricity bill, but also implicitly help power grids to reduce the cost of operations. So the question is, how do we do it? So the classic power system literature suggests you to formulate another hierarchical bi-level optimization problem that will find the optimal allocation of data center demands through through the network of data centers, where every demand will respect the limits of data centers, and will also make sure that aggregated demand is preserved. It's just allocated across the network, right? And this data center allocation would enter the optimal power flow problem I introduced before. It will respond with prices, and solving this problem in a closed loop, data centers basically explore this function of price as a function of data center allocations, this non-convex landscape of electricity prices, and get the optimal allocation of workloads in a power grid that minimizes the total electricity demand charge. The problem is that we don't really have too much information about actual power grids to restore this function using optimal power flow problem. So instead, what we suggested is to take all this information from dashboards and approximate the price function using neural networks. So neural networks are remarkably good in expressing nonlinear, non-convex functions as the one for electricity price. And what we can do, we can take the history of operations of data centers, look at their demands or loads, and map them directly to electricity charges from electricity market. And then instead of solving a bi-level optimization problem, we can solve a much simpler problem, optimization of a trained neural networks. Neural network, again, takes your demand allocation, maps it into electricity charge, and minimizing the charge while respecting the constraint sort of helps data centers to find the optimal allocation. And it works remarkably well. On this map, it's the same 118 bus system. And here, instead of actual LMPs, you see the difference of locational marginal prices. So you see that those nodes that used to be extremely expensive before, now by optimizing over trained neural networks that approximate the price, we managed to reduce locational marginal price at these nodes by $118 per megawatt hour by shifting the loads. And this is a remarkable effect. This is a different perspective on the same story. So we have a different operating conditions. Some of the operating conditions are very lightly loaded scenarios, so there is not much of coordination potential. Red bars here show you the baseline allocation. Green bars shows you the this improved allocation, that price responsive allocation of data center workloads in the power grid. But then when the system is heavily congested, there are a lot of coordination benefits from the strategy, and you can just see them by looking at the difference between some price agnostic allocation and data center price optimal allocation. All right, in a few minutes that is left for me, I want to quickly talk about distribution level energy storage solutions to smooth data centers. So again, remarkable growth of data centers, particularly in Virginia, where pretty much normal residential neighborhood can now look like this. There is a new neighbors, so you can have a nice view on the data center from your home, right? And everything is fine until you realize that the electricity consumption of data centers is extremely disruptive. So if you have any voltage problems or power quality problems in a data center, in a distribution grid, likely it can be attributed to this disruptive electricity consumption pattern of these data centers. So to solve this problem, we'll look into energy storage as a solution. So how we can deploy it? We can deploy it in different ways, but one natural way is to think of a data center as an electricity consumer, and behind the emitters there exists a storage unit that tries to smooth out the profile of electricity consumption that is observed by the grid. So it can be substation, or it can be a bus in the distribution grid. And G, that's what is observed by power system. And we like to use a storage to smooth it. So we cannot micromanage storage. So we need good control policies that can autonomously run storage units to smooth the load profile G. We can use a classic Brook control strategy that will take the measurements of data center demand and data NG and try to smooth consecutive consumptions of G. And a bit more proactive approach is to use feedback optimization strategy using gradient-based controllers like mix-saddle floor to take the same measurements and additionally penalize constraint violations. For example, if you like the ramping of these loads to be limited by some hard constraint, you can use the dual information on that constraint to penalize it. Okay, long story short, here is the results. You have original consumption of a data center without the use of storage, and then this blue trajectories here, it's this consumption seen by the grid, smoothed out by energy storage using a simple group control strategy. So the simple controllers that are already out there, they happen to be quite helpful in shaping the peaks and reducing the magnitude of this consumption. more proactive feedback optimization happens to be even better. So you see that it stabilizes the power consumption of the data centers, efficiently cuts these spikes, and so that the distribution grid sees a more smooth, more stable profile of electricity consumption. This is work in progress, and we are ready to share the first result relatively soon. All right, to sum up, today I talk about hierarchical optimization models for coordination spatial data center flexibility. There are a lot of coordination benefits that can be approximated using contextual regression approach. I also talked about how similar coordination benefits can be delivered by existing market mechanisms, right? Inherent incentives to move workloads from the parts of the grid that are expensive to less expensive parts, saving up to 50% of charge of data centers for electricity consumption in a very congested cases. And there are also distribution level energy storage solutions that help us to smooth DC loads and using gradient flow algorithms. Yeah, I think I will stop here. Thank you for attention. I'll be happy to take a few questions if time permits.
Hopefully you can hear us. There's a question. Go ahead, Adam.
All right. Well, I guess I had a couple of questions, but they all have to do with what information is needed to perform the kinds of optimizations you are talking about. So like in the first part of your talk, the kind of implied model, as I understand it, was that these data centers are working together, maybe owned by the same entity, so that you can like move load around, move jobs around between them. And so that's a very particular kind of coordination that does, if I understood correctly, sort of doesn't really work between competing data centers. But then some of the other things you discussed seem to make sense even for competing entities, or entities that aren't all owned by one, that aren't part of one organization. And there, I was really curious what the obstacles are in terms of information sharing to implementing these kinds of optimizations. So like for the pricing mechanisms, for example, how much information does one need about what's going on like inside the data centers to set the prices to get the kind of coordination effects that you were talking about?
Thank you, Adam, for your question. Yes, but let me start with information requirements, and I will go backwards where information requirements are very small. In this case, this energy storage can be installed by data center owners, right, that are concerned with the impact on the grid. The only information that is needed is the current electricity demand of the data center and the power observed by the grid from the previous timestamp. So all this information is available to data center operators, so as electricity consumers, and there is no barriers for information, right? So it's a very easy case. When we talk about markets, yes, information that is needed here is okay, this depends. In the solutions that we advocate, right, we need to train a neural network that will map our allocation decision of data centers in the power grid into electricity charge. All this information is available to data centers. So this is done. This is given by the history of their participation in the electricity market. So they have this records, the train neural network, and then the limits on data center consumption, maximum and minimum, is available to them. They also know the demand, overall demand for their services. So this information can be solved completely autonomously from grid operator. There is no information exchange. So, and this is a very attractive solution, right? Prices, again, are all known from dashboards. information can be approximated. In the first part, yes, it's more involved. We need to train coordination policy. We need to know a lot about data center constraints. We need to know a lot about grid constraints, right? Where do we get this information from, especially when a grid constraint is so classified and data center constraints are also not publicly available, right? So this is up to data centers and grid operators to discuss, honestly. I'm at the third party that look into this problem. Well, I can sort of build a synthetic case of New York ISO, kind of restore more or less the mapping from this special shift to operational conditions, solving some synthetic OP of optimal power flow problem. I can do it, right? But when it comes to deployment in the industry, there are a lot of barriers for information exchange, parameters of transmission lines, loads. So yeah, as we discussed before, differential privacy can be enabling technologies that does it. So we can convince system operators, okay, do not release the actual information, release approximate information about topology, grid parameters, and differential privacy algorithms can actually do this exchange. But again, thankfully, I'm not in charge for that. For these conversations, it's traditionally very difficult to source real-world data from power grids, right? But some differentially private synthetic test cases, I believe, can be intermediate solution to solve to this problem.
Let's get one quick question from Hendrik. Sorry for making everything quick, but we are not a little behind.
Well, it's a quick question. I was maybe you mentioned it, but so typically the two issues moving workloads in practice. But one is of course, especially if you think about foundation models and pre-training, that kind of stuff.
Yeah.
You got to move the data. So maybe that is what you meant by latency. I wasn't quite sure. And then the other one is, of course, in an ideal world, right? The data center, whatever the cloud provider, whoever it is, they want to have 100% utilization no matter what, right? So so their goal is to fill this up as much as they can. And so I'm wondering, well, maybe on the first one, are you considering at all sort of this issue that, some workloads can be moved, some cannot be moved because of, well, it takes a long time and there's actually substantial cost of moving it to another data center?
Yeah, thanks, Henry, for this wonderful question. So the task shifts first. They are workloads like large language models. So they can be pre-scheduled at different locations, right? It can they're training, but it can also be inference, right? You can. This is the workloads I'm talking about, and there are a lot of real-world examples of how it happens. For example, Google moves workloads not just across one ISO, not just across the United States, but globally. So they do it currently in response to emission. They want to minimize the carbon footprint of their workloads, and they globally across the planet Earth move these workloads around, right? This is a sort of a standard practice for them now. Talking about utilization of data centers, yes, you do want to utilize data centers to as much as possible. That makes sense. There is a rational need. The question is, you can plan this utilization, right? So if for a particular peak hour, so it's beneficial for ISO to reduce the load, right? You can coordinate with them, maybe get financially compensated. Most importantly, you want to be responsible for putting the grid down as a result of scheduling data centers in a very congested part of the grid, right? So you don't want to get this reputation as well. It's also extremely polluting and everything. You can coordinate it, right? The question is, how do you plan it, utilization? So as long as you can allocate it optimally under grid constraints, you can still achieve 100% utilization, but maybe not across all 24 hours horizon, but just less in times when the grid needs your help the most, right? This is all subject to negotiation, coordination. It happens At the level of distribution grid currently, Google reports very successful demand response programs where they peak shave the consumption of data centers. It happens. So let's just bring it to a high voltage grid as well. Yeah.
So the first question is actually was saying how big is a bundle of the service flow. So on one hand, how do we operate this? And so that within this assess the hosting capacity of the current user, you get the display, the body of your data centers. And perhaps at the same time, how we data center utilize the application, size, and the energy consumption. Please, almost more
Rest.
So let's start with just, I think something that was mentioned earlier, Virginia. So they have like around 550 data centers connected, and doing it around 140. And Massachusetts at lower 50, Connecticut at lower 60. So our starting point is in 0 in the region. So there has been a lot done, and there has been a lot of ways in which how do we integrate them into the system in the most efficient, effective way possible. Where it gets tricky, and I'm going to kind of come to a fork in the road here, is transmission and distribution. If you're connecting distribution centers, any IT center that has a load need, and you have a distribution system that has that capacity, that is your fastest route. It can be served, any infrastructure to be built, just to connect it in, that will be your fastest way to meet the need of who's looking to connect. So that's kind of point one. And that point one is interesting because if you look at, I think nationally we have around 46 different distribution areas in Massachusetts. You have some areas, and we have served 30, 40, 50 megawatts for some particular large customers. Then you have other areas, and they have much, much less capacity on the D system. So your ability to try to connect to the D system first is very subject to A, where it's at right now, and B, what's the plan for going ahead? Because right now we're talking all about the present, but in transmission planning land, we're like 5 years out, or 3 years out, 2 years out. So you're looking to the future all the time. So it's for the D system, where is it now, and where's it going? Let's break it in transmission. Hosting capacity. So this is a really tough one, and this has popped up years ago in the DER space. So if we're connecting distributed energy generation, we as a grid, along with many others, we create maps to show developers where you can connect against the D system. When you get into the transmission system, it gets a bit messier because it's so much more networked. But something useful and great that's happening as a function of Order 2023, big large gen study, which Ayse will be leading. I think a hosting capacity map is something that is being looked at in that space. And I think it can have multi-purpose. So for large loads, I think it could be used to that end too. However, I think the question I was asking Hendrik earlier was, it's so subject to the other factors. Because we've had discussions with developers, and again, the baseline for grid right now, we have hundreds and hundreds of load applications, but I'd say we have around 40 that are 1 megawatt and over. Our largest ones are 900 megawatts. And so you're meeting with large load customers constantly all the time now. And for the very large ones, where you can see the D system can't serve, you're seeing, again, how do we connect you? And then do they have the appetite for that kind of time frame to build to get you that? So I think if there are solutions here where storage, where demand response could be part of the picture at a bigger scale, I think that would be a good thing. And I think the last point, just in the address of that question was, I think harmonizing things is probably the hardest thing right now. Harmonizing things, and when I say harmonize, all the DER, all the first generation, all the large load, and all the natural load growth. How do you build the system the right way the first time without looking like a gold-plating system? Because that's the other dimension of the opposed viewpoint. As a grid operator, as a grid owner, you can say, we have data centers, Jen, you're going to propose solution X, and you have consumers saying, well, hang on, we don't agree that you're doing that there. That's not the right thing to do. It's not a prudent use of money because you're not guaranteed that's going to work or not. So getting that balance right between what's harmonious, what's effective for parties, and then what's prudent from a cost standpoint is tricky, but I think we're edging closer.
So I think Barry had a pretty good summary on this, questions there. So I just want to add a couple of points here. So ISO in England, I think you have to understand what's ISO in England's job, the major responsibility. So actually, the ISO has three major responsibilities. So one is grid operations, the other one is transmission planning, so not transmission planning, system planning, including transmission and resource adequacy assessment. The third one is administrating the market. So any resources coming to the system and want to participate in the wholesale electricity market and have to go through the interconnection process. And that pretty much, Barry had mentioned about this. So in order to have, let's say, data center come in, first of all, I want to declare that, ISO does not see a large load center yet. Okay, so a lot of data center connection come to Barry, to your places. So what happened is this. So when load try to connect to the system, they come to the utilities basically. So you have their own queue, and they will do the study, and they will come to the ISO when they're feeling that, when they feel that this is gonna impact the bulk electricity grid operations. That's where the coordination is gonna come from. Okay. So there's a blurry part there. When we say large load centers, and I think everybody knows that there are some proposals in Connecticut talking about like 300 megawatt large load. And from ISO perspective, that is a large load. And then there's a question, should that come to the ISO queue, or should it come to national grid? Okay, so there's a question. According to our current market rule, we'll see that according to our current tariff, there's no mention about this. So we talk about a lot of interconnection of generators, right? But there was no mention about what about the large load. So this unclear, a little bit unclear there. From that perspective, that will be a potentially rule changes if that comes to the ISO and they have to coordinate with, definitely we're going to coordinate with the TOs. So from hosting capacity perspective, and Barry mentioned that's important from the distribution side and even transmission side. We do not, at this moment, we do not pay too much attention on that because the losses from the distribution system. And definitely when there is an upgrade required, and definitely need coordination and especially related to cost allocation in terms of transmission upgrade. So that's the thing I want to add to that. And today I'm very happy to hear a lot of discussion on this grid flexibility and offered about it, the data center, and it's really interesting. Thank you.
Thanks. I just want to really emphasize when you talk about the large load customer, how absolutely unprecedented this situation is with large load customers. Barry, you were talking about this sort of survey, some 30 or 40 megawatt customers. 3 years ago, we thought that was a massive data center. And now people are showing up everywhere across the country asking for 400, 500, 1 gigawatts, 2 gigawatts. We don't have systems to accommodate that, as you were pointing out, then, like even wondering, okay, if we're at those sorts of levels, is that something that should be at the ISO level, even if your distribution system might be able to handle it? Just one additional anecdote that I think of, I'm from Nebraska originally. It's a hyperscaler building a data center outside of Lincoln, Nebraska. It's fully publicly known, kind of known that it's going to be about 400 megawatts is what they're aiming to scale to. The Lincoln Electric system that provides the electricity there, generation and the transmission system, or the distribution system, their total peak summer day load is about 820 megawatts. The hyperscaler came back to them shortly after they got the deal to do the 400 megawatt data center, and they're like, well, we were hoping maybe we could expand. And the story passed back to me from one of the city council members was they said, well, how much more do you need? And they were like, all of it. We need all of it. We need all of it. We need I mean, they didn't say all of it, but they said, we would like to expand to 800 or a gig. And so both the city council, the utility are just like, how do we even think about connecting, serving that load, how that relates to the sort of that's in the SVP area. Anyway, just the massive challenge that it has, and we're figuring out how to accommodate multiple large load interconnection requests. I feel like we're in a situation where the industry was about 5 years ago when we started to really get worried about the generation interconnection queues. I just never had to think about this before, this volume, this number and capacity, and now we're seeing it on the large load side.
So something I observed as a researcher working in this data center power grid intersection has been that, when we talk to people in the utility or ISO side, it is a question like, what do you use for planning? As a computer engineer, I like simulations, software. It seems to be an extremely fragmented space. Everybody is using something else. There is no common standards. I mean, it's not just a matter of having software from different vendors whatsoever. It's just not having any common data types and interfaces, etc. I think it's a very fragmented space, and we are talking about, like everybody mentioned, planning for hundreds of megawatts of data centers. Just wanted to throw it out there, like, is this something that we see maybe going forward? There could be a more common language among all the utilities for building planning software and planning methods.
Yeah, so, one quick question before moving on to the next topic, right? So let's focus on our state, Massachusetts. Right? So what kind of role do data centers play when it comes to planning the upgrade or expansion of the electric infrastructure?
So, and this kind of just goes back to some of the discussions from earlier. So when we look at flexibility first, with regard to that being something that's valuable and that's a benefit, so what are we solving for there? So right now we do have data centers subscribed into our demand response programs. And you can see them in two ways. So you've got flexible and inflexible. There are inflexible customers that do not want to subscribe into any program. And what's interesting is a lot of the load that our data centers actually require is something that I think our EPRI colleague referenced is the auxiliary power, is cooling. Like 40% is cooling. So that provides a potential benefit. If you integrate that into a geothermal loop, that could provide heating. So there is a benefit in that respect. From a battery standpoint, we know that Ireland, I'm not just saying this because I'm from Ireland, but they have a very future-facing policy for data centers. They mandate that you have to be subscribed into demand response. They mandate that you have to have some degree of storage that can be utilized. So what role? I think it should be a helpful role. I think it should be a helpful role, but that will only happen with some degree of policy converging. And in New England, it's hard because we've got 6 states and we've got a lot of things happening at the federal level. But I think if you have some just things happening at a policy level, that could then help unlock some of I think the technical issues become less difficult if the policy factors support. Because it's much easier working with technical folks to work on technical solutions than policy things. I find the policy things are much harder to get right. But everyone's nodding their head to yes, I agree. So I've got a room of supporters.
There's one call of technical people.
On that policy piece and the need for it, and some insensitive customers, and for the data center team at DOE, we had the opportunity to be talking both to utilities, ISOs, RTOs, and data center operators and the hyperscalers over the last year or so, and especially the AI training data center operators, the folks that want to rent to them, the hyperscalers that are using it, are basically zero cost sensitivity to the demand response, like not interested at any price. And I think the tradition, they're on a massive race to capture a new revenue stream that has the potential to be a few $1 trillion a year if AI really starts to pay off in a few years. And they're operating off, not going too much into it. I think what they have found and where the policy can come in is that their attitude would be like, okay, if somebody's saying you can only hook us up, if we agree to a demand response, we'll go somewhere else. Well, they're out of other places to go. Nobody has enough power for all the data center demand that there is, right? There's not, ERCOT is oversubscribed, Northern Virginia is oversubscribed, that it just doesn't exist. And so I think there's a real opportunity to help figure out that policy space along with the technical people too. How to, and I think we've seen that in the interest that the Duke Nicholas School paper received earlier this year, that there is this appetite to figure that out at the policy level and perhaps more from the customer level of the hyperscalers, because they're just that power is out there.
So it's interesting note about the insensitivity to demand response. Basically, demand response, when you do it, you get money benefits, and it's like substantial benefits in terms of the percentage of electricity cost. So when one of my former students and I started thinking about commercialization of this demand response thing that we've been doing on data center side, we started talking to people, and I thought like, hey, here's like real money benefits. You can save money. I thought people would be like, yay, and they were like shrugging instead. So that's one problem, right? So the incentives are there, but it's not being used. One emerging incentive that is gaining traction though is there are some pilots in the country. I don't know about other places in the world, probably there is too, is faster interconnection. So if you do flexibility, there might be opportunity to connect faster. And that seems to be resonating with some of the bigger players in the data center space. Of course, like it's pilots, like nothing is set yet.
Okay.
Yeah, I just want to start some stuff from the ISO perspective. Talk about the incentives. You talk about demand response incentive, right? So currently, for ISO, you already have the demand response program. And from really incentive perspective, compared to other technology, demand response program is already getting incentives, meaning getting benefit. The reason is that under the current demand response program, not only we call double compensation, that's already happening. So what is really double compensation means that any demand response program, they get compensated by the demand reduction they achieve during the dispatching order, right? So there's an amount of work, and they will get paid by the LMP. But at the same time, from utility perspective, they're getting net metering benefit. So that's what we call double compensation. So currently, it's different from any of other type of resources. Demand response get double compensation. If you look at, for example, the DERs, the distributed energy resources, okay, and DER aggregation, and for end of fall 2022. If it's not demand response, they are not getting double compensation. So only one that demand response get double compensation. So that's for federal level, actually they do get incentive there. Of course, we want more demand response. Right? That's all gonna be from system. You're gonna have a great, benefit for the customer for the system reliability. That's definitely for sure. How do we incentivize them? I'm not quite sure. Because currently, if you look at ISO New England system, we got about 500 megawatt of price response to demand response. Right? So that is, originally we're thinking that, we should get more because, with this kind of incentive, they should get more. And there are different other type of resources, DRs, for example, the government, the states actually have this, we call the E program. Sorry, I couldn't remember the full name. Do you remember what the E is? Energy efficiency, sorry. Energy efficiency. That's actually a big chunk of demand response. In fact, we couldn't call it demand response, but it is. It's like the energy efficiency program. For example, you go to the lighting and you change to the LED. That's what we call demand response. But that's a kind of permanent, right? It's not basically once you change it, it's gone. That's it. It's not like dispatchable, not flexible. The only one that is flexible, which is, which is the, you have a behind meter battery. For example, you can change. For example, the solar generation, those type of things. That is actually dispatchable, kind of dispatchable. From state perspective, do you want to push forward the demand response, especially, for example, I think Massachusetts had a promotion in terms of storage. For example, they promote the storage installation, and we also have the federal IRA, right? So the solar, battery installation, all this can be combined into demand response program, and that's incentive. I know that in certain area, for example, the IRA actually huge impact in terms of energy storage installation. That's for sure. Not sure about the data center development. I know that the biggest challenge, in fact, is from tax incentives. And I think last year Massachusetts, passed the bill and to incentivize the data center development. I think that it actually is a game changer. We don't know how many gonna come, but the one in Connecticut, the one in Westfield, Massachusetts, they all proposed, right? But we have not known, the actual amount. Yeah. And I'm assuming that there are other also related data center development is related to, I think there is a FERC rulings on pending for the PJM. That was a co-location with data center with, with the existing site, for example, nuclear site. So we're watching on the policy decision there.
Perfect, thank you. So we mentioned several times the term flexibility. So what's the definition of flexibility from a power system perspective and data center perspective? And how do we quantify flexibility? Who would like to start?
I can start. So from the data center side, flexibility means being able to regulate its power. So for an emergency demand response scenario, when the grid has a lot of peak demand, this would mean flexibility would refer to a data center reducing its power consumption for a predetermined amount of time, a predetermined amount of power. So an example would be compared to your base load, give you a several hours heads up, and then data center is going to reduce by 20% or 25% for the next couple of hours and then bring it back up. So that's one example of flexibility. Emergency demand response programs exist in a lot of different regions. Another example would be to not just reduce when needed, but to do kind of continuous demand response up and down. There's, for instance, regulation of down program in ERCOT. There's regulation service resource program in PJM. So in this case, on a second granularity, data center flexibility would mean to be able to go up and down within some error margin of the required signal. So I said, this is what flexibility means, but even on the data center side, there's no one description, which is kind of interesting.
I don't have anything to add on the definition of flexibility, but just want to add that, I talked about the people not being cost insensitive to doing flexibility programs. They are absolutely sensitive to being interested to doing them if it means faster time to power. And so that's why this is such a unique opportunity now. So the more recent conversations, both the operators, the utilities are trying to figure out how can we structure these things so that we can get more data centers hooked up in the next 2 to 3 years and not having to wait to that 5 or 6 out. So I wanted to make that caveat to my already used in.
Yeah, and I'll just add 2 things quick. So predetermined is like I guess time then, because we can have cloud cover now that can majorly swing how the system responds, and it would be how comfortable or uncomfortable a data center would be in the shorter time frame in impacting. So that flexibility within flexibility, like so predetermined means 3 days. If we come to you, a day out and say, can you do this? It's how flexible is the flexibility program. We're going to Inception now. And another piece then is just how does that factor into the data center's emergency response plan? Because if they're using storage to make sure they have power for core activities, if they're involved in demand response, how much are they willing to take a risk? Because that's a big one, and I guess we're finding in speaking to so many, there's a lot of not knowing the answer to that question, and I think that sometimes gets in the way of data centers making decisions on what to do next.
Yeah, I mean, you pretty hear all the discussion about the flexibility. So I just want to add one point there is, flexibility, is a way you change your power consumption, right? That is basically what the flexibility means. The important thing is about the time, right? There's different time scales. And you mentioned that the regulation time frame, right? That's one thing. And we also talk about the, from grid balancing perspective, I'm talking about ramping capability. You can talk about, 10 minutes spinning reserve, what we call spinning reserve. And from ISO linear perspective, you have the answer service, meaning spinning reserve, 10 minutes spinning reserve, 10 minute non-spinning spinning reserve, 30 minute reserve, operating reserve. And you can also about sustainability, for example, can this kind of action be flexible enough such as sustain an hour or 90 minutes or 240 minutes. So those are kind of flexibility we're looking for. We're also looking at, for example, for day ahead time frame. For example, people who say, "Hey, I'm demand response problem. I want to be, my load can be interrupted for 30 minutes, but for example, with 30-minute, notification time, but I can sustain only for 60 minutes. So those kind of flexibility, I would say, attributes need to be recognized. The more flexible one will be that anytime I want you to respond, you can respond. That'll be the greatest one, right? Apparently, we were not going to be able to do it. How we quantify them, it is a big question. And all this response, will be pretty defined in the market products, and we need to do the auditing. For example, for the generators, for example, they are able to provide offline capability, for example, in 30 minutes. We're probably going to call them. So even though there's no demand, no event happening, but we will call them. We say this auditing process, we want you to start in 10 minutes, and you need to demonstrate that you will be able to start. So those are kind of quantification and auditing process. For the regulation capability, for example, we send this, regulation signal, you need to respond, and each one will get a score. If you didn't perform, then we know that you're not being able to respond to those fast signals. So those are the kind of things we're doing. Hard question about demand response capability. It is between demand response actually is their capability is calculated based on their baseline. And I think you might already heard a lot of questions about how you would determine the baseline. I mean, this is I would say it is still some questions related to how demand response baseline be determined and accurately determined. I think that's a question. Even though everybody had that methodology, but there's still way to improve. Thank you.
Perfect. But before moving further, let's drill down on this issue more. So, do you think that you can follow the same auditing and market process that you're using with generators for data centers, just by treating them as negative generation, if you wish? Or do you think that we need new market mechanisms specifically tailored to data centers?
Yeah, I can start with that. A good question. I will say that some of the demand response program, I think you probably don't need it. I say that the current market rule, especially in India, I think right, should cover that. But if it's a large load, maybe certain investigation need to be need to be done there. The reason I'm saying is that I heard what I heard. I don't know exactly, you know, because they're not coming to the ISO yet. So the demand not demand, the data center coming in really different configuration, I would say that. But sometimes they say that it can be purely behind meter, 100% behind meter. Some say is in front of meter, 100% front meter. And some say that maybe, you know, part of the, partially front meter, partially behind meter, and there's an emergency operation that they can switch. They can rely on the grid. So depending on how they operate and how we're gonna, whether our existing rule can be able to, I would say, is able to accommodate all the different kind of configurations. I think it need additional investigation. There's another point I want to bring up to your attention. Is DR, data center itself, especially today, I think Vladimir mentioned about the load shifting. If load shifting flexibility is available to the ISO, and it helps reduce the cost, reduce congestion, reduce the cost. I mean, that's a fantastic, opportunity to incorporate that kind of flexibility into the market. And the current market rule is silent. We don't have that capability, and that might need a new market design, a new market model, and potentially a new market product. Thank you.
I'll add 2 quick points. So one is, so for transmission for national grid, weirdly, I can't serve a data center directly because our distribution company have the franchise rights. So weirdly, all data centers will go through our distribution. So we work through them with that. And we've talked to all of the utilities in the PGM area who are kind of leading, and a lot of our practices are very, very similar. All that differs is jurisdictional rules and how do we optimize doing the same things in this space. And I'm saying that out loud to make my second point. So to answer your question, Emiliano, I think yes, because, and if you ask me why, I'd say the scale. We have around 3 gigawatts right now of data centers, Eversource, roughly the same or a little more. So if we're looking for opportunities to maximize or optimize how we integrate that the system, would seem, I guess, just to make absolutely doubly sure we don't miss something, maybe we look at just how markets are framed or set up. Because I think there is opportunity there. There's also enormous risk there. So I think waiting in that space, eyes wide open, then utilizing some of the tools and concepts used today. I think some of the points and tools used today are will be massively useful to understand some of this. But last point on policy, there's just enormous uncertainty with what's happening. And that gets hard then, because as you're taking your building blocks to build your future, half them or more won't work out, so that gets challenging.
Quickly, so on the specifics of a new market design, that's well outside of my area of expertise, and enough outside of it that I won't say anything about it, as opposed to all the other things that I talk about that are outside of my expertise. But I will. One thing I mentioned that I think is an additional wrinkle to thinking about that, and I find the argument that we need something new compelling is that, again, in the conversations that we had with data center developers of all sizes, including the hyperscalers that operate their own, is that they had the typical message is that they have zero interest in managing a generation resource. So they're not opposed to that system. They're not opposed to figuring out how to make it work. They don't want to take on the additional risk of managing a generation resource that's doing something other than just serving as a traditional backup. So I say that it's like potential business opportunity for people to figure out how to square that with those sites and utilities and operating these resources.
It's good to be able to take questions later.
Yeah, perhaps. I mean, I do have another question. Well, let's see. Is there any questions from the audience or from Zoom? Although I don't know how to pull up Zoom. But... Yes, please.
Yeah, thanks for the great discussion. I'm Tyler Horse from Duke. So in the PJM co-location docket, one of the big issues is whether all new loads should be treated as network loads or a different type of non-network load. And what's basically been illuminated is that PJM doesn't really offer any service tier that isn't network load. And so I'm curious, I don't expect you necessarily followed all the back and forth in there, but I'm curious if you think that ISO New England and maybe at the national grid level too, that you might need fundamentally new transmission service tiers that kind of get reflected in the planning realm. Because we've been talking a lot about the DR realm, sort of in the markets, but to recognize it in the planning realm, don't we need some sort of new service tier if in fact there's substantial flexibility, or do you think it could be treated as a network load?
What's going? I'm going to pass that one. So no, I'll take that one. What we have found in this area is that if you have just one customer off what you build, it's more reasonable that they pay for everything prompted, because they're the sole beneficiary of it. Where it gets weird is the point you're making. So you're going to build a substation, 75% will be used for a data center, and 25% will be used for the community. And of that community need, say 10% is DER. Who pays for what, right? And that's at the heart of the PGM factor. So what we've been doing so far is, number one, trying to bump up the load needs with our distribution needs of the area, and then see what does that look like. And then relative to that looks like, sometimes the cost allocation, if things progress, it's actually pretty clear. Transformer X for community, transformer Y for the data center. And sometimes it's not the case. And as you integrate these needs to, and coming up with a way to cost allocate, you're mindful all the while the data center or the first generation or they could drop out. And if that happens, does that make your solution then for that area not valid? Does it make it non-prudent for your consumers, your customers? So it's a really hard one, and we're paying close attention to that. And I think in the PGA area, again, they have really helped that state do well for data centers. But do you get every single question right all along the way? Very hard to know. But you're watching that very closely, and we're just trying to do it on a case-by-case basis. Well, unfortunately, we are out of time, so we should thank our outstanding panelists. And I will let Ayse tell you about the next logistics.
Yeah. So the next exciting step is lunch. It's outside. And so we have until, let's say, 1:05 for lunch. So then there'll be 2 breakout sessions. One will be in this room. One of them will focus on this data sharing, collaboration, and privacy challenges, and that's going to be here. And the other breakout session will be in the 16th floor. We just go up. And that's going to be on this data center power grid collusion, opportunities and challenges. And in both sessions, we prepared it such that there are some exciting, thought-provoking exercises for people to work on, and hopefully will lead to great ideas. And then the breakouts will take from 1:05 to 2 p.m. And then after 2 p.m., everybody's back here to discuss the outcomes and next steps. Thank you. Food is outside, and the restrooms are on this side. See you around. So we had 2 breakout sessions. Thanks for all the productive discussions. So the goal now is to kind of do a report out, informal, and have more discussion. And I'd like to, at the end of the day, come up with a few action items for us. And, as practical as possible, like build an email list so that all these people communicate. It's a simple one, but I just gave it as an example. Or,
start a project in this direction, or lead a consortium that's going to enable privacy preserving data sharing. So basically practical things that we can think about. So that's the goal. Or go have a meeting with all the stakeholders to show them the great potential of flexibility. So it can be anything, can be small that we can do today, or can be something that we would need to work on it for a while. So that's our goal. With that in mind, Emiliano, do you want to present our breakout, or should I just? Okay. So Fatih helped put together a few notes. This is by no means comprehensive of the discussions we had. It was really excellent discussions. And just to remind everybody, our breakout was on data center and grid collaboration. Basically, what are the opportunities and challenges both on the data center side and on the grid side? So an important aspect was that ISOs never planned for flexible loads before. So this was highlighted multiple times throughout the day, but basically what's happening right now is unprecedented in many ways. So we haven't seen it before, so we need to do some new things. New services need to be planned for data centers, essentially. DC over there is not direct current, but data center. And so one of the obstacles in this space has been that utilization, like tech companies, data center companies, they want to keep their AI utilization high. They don't have much room for flexibility, they say. But some of the participants said that when you talk to people in detail, this is not quite the case. So it's not necessarily at 100% at all data centers, so there's room. In fact, one of the discussions that came up was that a lot of users are ready for flexibility. A lot of users know that their workloads can be delayed or paused for a short amount of time, and they don't really care, and they would welcome the opportunity, especially if it leads to faster connection. So this was again emphasized throughout the day, but also in the breakout session. Policy aspect, basically public-facing piece is important and needed here. Like I mentioned, a lot of users are ready for flexibility, especially if it results in some benefits for them. This could be savings in terms of how much it costs to pay for electricity or how much it costs to do AI, but it could be also just faster adoption of AI, or just having access to AI in the first place, right? So, and a lot of users are ready for flexibility. So it seems like users are not the bottleneck here, but some other stakeholders might be. And data center flexibility can enable faster adoption of AI data centers as well as other things. So it's not just data center flexibility for data centers alone. It's actually this kind of flexibility can enable adoption of, for instance, more green energy. It can enable other flexible users of electricity to join and the like. So we talked about two specific questions. So what are possible ways to incentivize data centers? Because one thing that came up several times again throughout the day was that data centers are not necessarily incentivized by money back options offered in current demand response programs. So one important point that came up was that existing demand response programs are not set in stone. It's possible to rethink some of these demand response programs and create incentives. It's not a one size fits all solution. Different signals could be provided for different kinds of users. This could be based on who's joining to what kind of grid, at what point of that grid's history. It could be depending on the size of the load, the flexibility of the load, etc. So there's some room for improvements in existing demand response programs and markets. One thing that was highlighted was that flexible data center, interconnecting flexible data centers faster, like the Flex Connect pilot in PG&E in California, is the obvious product for incentivizing, because everybody wants more AI, and this is being piloted. There's no existing mechanism in any market right now, but it's being piloted. So this is the obvious product for incentivizing, because even though people may not care about money back from demand response, they care about being connected faster in their data center. So Flex Connect program, you can check it out. They have some info on the web. PG&E
There are two PGs. One is Portland, one is Pacific. This is Pacific. Pacific Gas and Electric has this pilot program. We also talked about some hurdles in Massachusetts and other states. So it came up that this is more of this being like the optimization of the grid in a better way for data centers, but also generally for resilience, for growth, for better planning, is more a market issue than a technical issue. It takes a while to get everybody to agree. So it seems like there's a lot of things done on the technical front, but very few of them are making it into actual practice. So there seems to be a big gap there. And one of the issues that was discussed in this is that AI is also not necessarily, while exciting, may not be reliable and safe enough to deploy, as these are safety critical systems at the end. We are talking about power grid infrastructure. So it might be easier to deploy AI in cases where, if your AI gives you a wrong response, it's not the end of the world. Whereas in the power grid, this would be considered potentially traumatic or potentially bad event or a cascaded bad event. So those are some of the things we discussed. We put these into these quick slides, but Ajay, Adam, do you want to put slides on or just discuss?
So I think Shada and Tom, we had two separate discussion groups.
Shada, do you have the link? If you just copy paste the slides into that, I can refresh it from here. It's in the Slack channel. Super. Yeah, you can come over. Yeah, here. Right.
So hi everyone, I'm Shada from this big project, working with Professor Joshi. So this is some part of the data sharing.
To speak at the microphone.
You're right. Can you hear me? I guess so. This is one part of the breakout session on data sharing. My friend Connor will also share some of the thoughts related more of the privacy aspect. So we discussed types of info that can be shared if we do collaboration, and also discussed if collaboration is ever possible on this data center demand response programs, thinking on the law perspective, thanks to Keith, and also the cryptography perspective with Professors Joshi and Varya. So the data centers can share their workload types, client types, power usages, but mostly when we think of the power utilization, we were focused on the power usage type because those are kind of a little bit more irrelevant. This data is sensitive depending on the client. Clients are, if they are big companies, usually a little bit more sensitive about sharing their data. Of course, if we think of governmental organizations, this can be less sensitive because everything is happening inside, but usually big companies do not want to share. So we need to give them big incentives to share that data. And this incentive to collaborate is usually money. So when we are talking about peak power usages, power utilization, sustainability, and also the bigger part that we think in terms of in the research community, green computing. But when we think of the industrial perspective, I guess they all boil down to money because these all, at the end of the day, goes back to the discussion in terms of the data centers, which are really big companies. So, but obviously in the research community, we think we give a lot more perspective from the type of green computing. And after this point, we a little bit went off topic and discussed some other issues depending on our own research interests. So one question was that demand response program is not just a single black box where we think about everything in terms of just power utilization. There are a lot of different smaller parts. Data centers are huge systems. And Keith mentioned the work from Berkeley. I couldn't cite it here right now, but I can add it to the slide deck, where this group from Berkeley modeled the whole data center demand response programs, where we don't just think about the utilization of power, but also we model the whole processors, memory units, and of course the heating and cooling problems to better quantify what is happening inside a data center. And at the end of the day, we need an end-to-end model to talk about the costs and benefits of any research project. We also talked about that efficient power usage is not the only goal. Keith also made us aware that peak power usage is not the same as just power utilization. So depending on the climate, for example, if we are living in the very north or south, companies need to regulate their peak power usage days depending on the climate, and this affects their cooling schedule. For example, at some times of the year, these can overlap. The days that you need to shut down your system for some climate-related regulations, but those days might be the top power utilization days. So with these two concerning points, we stated that we came into the conclusion that data center demand response is just the small topic that we discussed today, but it also leads to several broader different discussions. Thank you. That was it from me.
And I just have a little bit more information to share about what we discussed during our breakout session. And if people from the breakout sessions want to add a little bit more information, certainly feel free to do so.
Just refresh. That should work.
Sure. Oh, sorry.
Is it in that same link?
Yeah, it should be at the same link that should.
The
The
URL and
Yeah, should copy Connor's slide over. Connor, just wait a second.
Sure. Okay, it looks like it shows up now. And just as a note, like these notes are a little like they're not as optimized for slides as some notes are. In any case, so we talked about like the issues that can arise when you're doing real-time sharing among data centers, and we also briefly discussed like creating energy use data sets for research. And these notes focus a little bit more on like the challenges of doing these things. We learned some good ideas about like techniques for encouraging this sort of sharing as well. So some challenges that arise are like companies are very reluctant to share how much power is being used for different computational tasks. So as an example, companies are very reluctant to say, okay, 30% of if they're serving some LLM from a data center, they're generally reluctant to say we're using like 30% of our power for serving compute for these LLMs, and we're using 70% of our power for doing inference. That sort of data is like considered a trade secret, and companies are very reluctant to share that style of data. And they're similarly sort of reluctant to share real-time information about what sort of data is being, what sort of energy use is being experienced by the data center. On the flip side, though, data centers are hugely incentivized to share data if that data will somehow allow them to be connected to the grid much more quickly than they'd otherwise be able to be connected. So oftentimes there's like a 5 to 7 year-ish waiting time between when a company kind of comes up with the request to make a data center and then ultimately sees that data center get connected to the grid. So companies are very incentivized by structures that are put in place that could allow them to join the grid more quickly. So if data sharing might get a company connected to a grid more quickly, the company is going to be, generally speaking, very willing to share that data. Then the second point that we talked about was like dealt with creating these energy use data sets for research. And just one point that I sort of want to note is that there's a lot of reluctance, again, about creating these sorts of data sets. So there was a recent effort by the Energy Information Administration to get more data on how crypto miners are using power. And there was just a lot of pushback surrounding the creation of this data set. Ultimately, I think the data set creation did not happen. And that mainly stemmed from a lot of lobbying efforts by these crypto mining companies that complained about government overreach, and a lot of the motivation for these complaints was that just the crypto mining companies did not want the public to like become aware of how non-environmentally friendly crypto mining is. So there are a lot of challenges in terms of how we might encourage companies to share data about what their power usage is. But one huge incentive that we have to play with is just the fact that if a company, if there's something that companies are generally very, very willing to take steps that can allow them to get connected to the grid more quickly. So I think that basically covers what was discussed during this breakout. If people from these breakouts want to add any more information, though, go ahead.
Thank you. So our
So then the other group. Oh,
yes.
Okay. Sorry.
Sorry.
No, it's all good. I don't have slides, but I was gonna share some information from the other breakout group that we had in our room. And so we did go a little bit kind of off topic, so we didn't discuss as much about maybe the questions in part one, but we were kind of on the general topic of basically like if you want to increase participation in these flex programs, can you use some sort of central party to do this that kind of does something with, in a collaboration with a bunch of data centers? And we were on that topic because, as several people mentioned, the price incentives are not necessarily that enticing for data centers, especially ones that have like pretty valuable workloads that they don't want to mess up. And so one of the ideas that was floated was maybe a central party could run some sort of power market between the data centers and leverage that to participate in these flex programs on the side. And then that way there is an increased participation in the flex programs, and the data centers are actually getting the incentives that they want, which is kind of the power. Maybe they get like IOUs or something like that from other data centers. And so that was one idea. And then, right. Then we kind of moved on to the second part of the breakout, which was what is the information being shared right now and what more information could be useful in the future and what academic research could help. And so in terms of the information being shared right now, there's power usage information, power efficiency information, and dashboards that inform clients about the locations of data centers and the services that a company offers and things like that. But the question was kind of what other data might we need? And one of the ideas was about kind of load profiles and getting finer grained information about load profiles and how this could potentially become available. And we were discussing whether synthetic data about load profiles, since ISOs already have this information, but they can't share it, maybe some sort of like private model of these load profiles could be useful to kind of train forecasting models on. And one of the questions was, what kind of forecasting would we want to kind of use as a benchmark for these synthetic data sets? And, is there a possibility of then verifying the forecasts of such a forecasting model on the real data somehow privately? And then that kind of proves the usability of the forecasting models that you might train. So, yeah. That was most of what we discussed. But if anybody in the group would like to add more information to the stuff that we were talking about. Yeah.
Thank you.
Yeah, thank you so much.
So I don't know how it works with the long thing. Let's see. So in the remaining little time, I'd like to just open the floor for any thoughts, especially considering what we can do. As a great group here, we have people representing ISOs and utilities, we have researchers from different domains, people looking into power grid optimization, from data centers, from software to hardware. So great community. How can we work together to hopefully help resolve some of these challenges? I hear echo, by the way, but not sure. Anyway, I was just going to check Zoom to see if there's anybody there. Okay, do we have a few participants? So if anybody would like to speak on Zoom, let me know and I can see it. And hopefully you can hear when people speak. Yeah.
So maybe two points. So one, some really interesting things discussed today. And if you look at the developed community, I do think part of not seeing the same value from that side of it is they don't understand. Because in dealing with some of these calls, you have two common entities appear, investors and people who do it. So there's commonly an absence of criteria of what they should be looking at to make it viable and profitable. So I guess the question I'd ask to see if it exists, I'd love to see it, and if not, then maybe it's not to me somewhere, is does a document exist somewhere to show what are the steps towards that you should take, maybe if someone is going to build a data center, of what are the appropriate assumptions I should take into account when building, whether it's voltage level, whether it's size. We talked about today, output sizing, demand response, because as a utility, you answer all the questions they ask, but you can't steer them, and because some of it's their judgment. What kind of risk do you want to take as a company? And I don't know where some of these folks go to after they speak to us, because I don't know a document or an entity. There are forums like nationally, there are forums internationally, but I mean, it'd be wonderful if there was some kind of prescriptive documents or YouTube videos that we follow my DIY on what are the steps I should take to see is this viable or not, or should I back away? Because I think there's a lot of noise in the industry as well now, and I think part of this could help reduce that and then enhance some folks to make fast those were real.
Thank you. Thank you. Comments, questions, thoughts? What's the next step for us? Yes, go ahead, then.
So, the themes that came up in the discussions, our breakout broke into two sub breakouts, and I was sort of bouncing around between them. But one of them was sort of the extent to which the benefits of demand response schemes and collaboration could be realized solely with sort of market-based mechanisms and sort of pricing, and whether or not that is a way. So the kind of attractiveness of this is that it's a way of eliciting information from people based on the response to prices that doesn't involve them sort of explicitly sharing, internal details. And so, like, one point that came up in both discussions and also in the earlier panel was that for many workloads, the customers are not price sensitive for like AI training, for example, and inference even, and so. But one of the ideas that was floated was to trade something else that is more valuable, like to sort of think about setting up a mechanism where the data centers sort of trade power availability with each other. So rather than using sort of money as the mechanism, actually sort of trade the ability to trade compute, basically, or rather power, the ability to power compute. And so I thought that was an interesting set of ideas to explore, whether or not that's a different venue for collaboration that wouldn't require explicit data sharing per se, but would elicit a lot of information about internal computations. So anyway, that was one thing.
So maybe before you continue, one note that was interesting that I meant to mention in the breakout summary, but I forgot. There was a person who is managing data centers, university data centers. And what he mentioned was that, I'm trying to keep the lights on and you are talking about the city's lighting kind of thing. So this, we kind of take this for granted that, the data center companies are not price sensitive. That's completely true for big companies, but there's a ton of others who are trying to get AI, and it's super expensive. So I would bet that they are very price sensitive. But it's just like they are probably not sitting at the table. So I think that's interesting to think about, like not the entire data center space is compromised only of big companies, and a lot of smaller entities are having a lot of issues scaling their operations for AI, for running AI, because it's expensive.
Yeah, one of the ways that came up in the discussions was the suggestion that to the extent one does try to set up some kind of data sharing agreement, that it be broken down by, in some sense, by categories, like there could be sort of lower value and higher value workloads where, or basically just more, some workloads are more flexible and others are not, and just sort of trying to possibly just explore, partition those and think of them as sort of totally different categories might be useful in terms of focusing where, finding the places where price sensitivity is, where there is sort of, where demand response is likely to be incentive compatible.
Just very short comment there. I think you mentioned that there are data centers, not like constrained demand response. But they consider that reliable supply. You also, I think, the workshop also demonstrated that there are technically feasible. You also mentioned about how incentivize people and talk about one. I'm just wondering whether you can talk about it not because they basically, data center.
Yep. That's a great idea. Actually, one thing Emiliano and I are collaborating on is this, data center demand response, but how to apply this to the case of Massachusetts, for instance, like basically pick the specifics of Massachusetts. We didn't really get into cost-benefit analysis from the data center perspective, but it would be good to put it out there. I don't know if this is interest to Tyler as well. He's been working on the analysis of flexibility and what that would mean for the grid from a practical standpoint, but maybe that's one of the next steps, that we need to pick a few cases, some specific data centers and specific states, and show the benefits of this, right, for people to move towards adoption. Because there seems to be a lot of prejudice, like we can't do that because we have to have high utilization, or we can't do that because it's not worth the effort, the monetary gain is not enough. And a lot of these may not be fully correct. So perhaps it's good to, like you are suggesting, do a study.
Yeah, I just want to echo. I think if either Massachusetts and or I assume New England or National Grid or one of the other lives around DC could, or together, create what would really be the first product in the country and maybe the world that would, credibly quantify the trade-off with flexibility in exchange for faster interconnection, and come up with a framework for doing that. Even if it's not used here, which maybe it would be if it was a attractive product, but I think it would make a major contribution in establishing a model that other jurisdictions can use where there is a lot more demand, because we really need that right now, and it's completely lacking.
And every state has interesting things as well. For instance, Massachusetts is a leader in green energy. So Massachusetts has a lot of stakes in continuing green energy adoption. So flexibility also helps with adopting green energy in some ways, or to sustain the state's decarbonization goals. For instance, an example is that Massachusetts uses peaker plants natural gas plants essentially to make up for these peaks. So they turn on some additional gas plants, and we have a winter peak as well because of successful electrification of home energy. What I think about when I think about this data center growth coming up in Massachusetts, I think about these two things together. Potentially, flexibility in data centers could enable reducing the peaker plant usage. So it would be really interesting to do more case studies like this for specific states with specific ISOs, specific data centers even. I saw a hand over there. Yeah.
Data sharing is not there in data centers. I've seen that in healthcare industry as well. Same issue, right? Data sharing, but there are industries where people are sharing. One thing that people do is people don't Meta. They share the Llama model. People have developed the model and then made something. But try to understand why do they share it to the wider world and what's the greater good they were trying to aim. If you were looking at outside the data center space, there are very successful use cases of data sharing and trying to understand how they benefit and trying to make the same case here. Because unless we are able to show that there are these many millions of dollars to be made or saved, it's very hard to convince people to even do data. They see the value, but they don't see the value in dollars. And then the whole idea of how to use security learning. So looking outside the data center space for inspiration also.
So I don't know if this came up in the breakouts, but if there was a repository that's privacy preserving, and let's say we built this, because I believe there is a technology through expertise here to build something like that, why would a company who has data contribute beyond, sharing, like similar to open source models? Would they get something out of it? For instance, like by contributing data, you also have access to seeing the other data in a privacy preserving way. Maybe that would help them optimize their operation in some way, right? So are there things that data centers or companies sharing this data can get? Or by sharing data, you are promised something. I don't know what that is, but I saw a hand from Hendrik first, and then
That's a good question. Follow up on what Tyler suggested. Very interesting. Maybe approve but that would require some regulated statistic, right? So maybe that is missing. It was a great idea to say, okay, let's trade flexibility, some of these things fast forward. I think that would really work.
Yeah, and that's the problem. We have no service tier like that really anywhere in the country except for the pilot scale program that PG&E created, Flex Connect. So, I think you could have a load serving entity do this independently without regulator approval, at least as a pilot or even a non-pilot. But given the scale of these loads, it seems like where this is going is there is going to be some FERC jurisdiction because they're going to have major wholesale market implications. So you're probably inevitably going to have some degree of like the ISOs and the FERC involved. But I think you could start at any level. You can start at the state level because arguably a substantial portion of it is still state jurisdictional, or you could start at the LLC level, or you could start at the ISO level, which is kind of what's happened in PJM. We just need to get people moving because we're not moving right now.
Just on the cost analysis, so this real example, we have one data center with 10 routes to get to their location that range from 70 million to 150 million, and that's a space move because you're undergrounding almost everywhere. So to demonstrate a cost benefit analysis, I think others involved will help frame your assumptions and caveats better. Because there's tons of judgment going into cost analysis when you set the diverse range of scenarios. So I think it's an excellent idea, but the more involved, I think the better, because otherwise you can sink anything and it produces because there's so many variables.
Thank you. Nathan?
Yeah, so I was interested in the Berkeley study about sharing all of this stuff, as well as the earlier talk by Professor Dvorkin on the New York ISO and space-time moving of resources around, and maybe start thinking about whether the information, the data that is transmitted, that's being computed in places, is restricted to ISOs. Like, for example, the Berkeley study was that Cal ISO specific, and why wouldn't it be possible to just use fiber optic to send, to expand the space-time sharing across the entire continent if the efficiency of energy with fiber optic transmission is like quite good compared to electrons? You know, whether that's part of the conversation, and it makes me think like you actually get 6 more hours of sunlight by east to west coast solar energy. So, and we think it's even bigger in terms of how the information is moving around.
Interesting. That's right. Yeah. So also geographically, this is a huge country, like you said. So there's a lot of advantages potentially that some other countries may not have in moving things around.
Right. And what other federal regulator is involved? This work is energy, not data. So is it the FCC that would be thinking involved in such a regulation or not?
Other thoughts? So if there was a follow-up to this in terms of like some sort of a consortium, another event, a meeting, a paper, project, what would that look like? Like, what would it look like for you, ideally, to be well worth of your time and to get something out of it? Go ahead. Nathan, I think. Yeah.
Well, the grid being a socio-technical system, I would love to see surveys or to regular ratepayers or private researchers or others that are end users to query them about their own intentional flexibility with the jobs that they put in, whether in Google searches or data processing jobs.
So understanding user flexibility better.
Yes.
From the end users. So already it was suggested that, doing what if scenario or cost benefit analysis of flexibility would be something interesting to a number of people here, I guess. Any other thoughts? Yes.
So one thing that came up in the discussions that in terms of data sharing, one of the like relatively high value places to look would be sharing load profile data. This is Hendrik, which is shared in some countries in more detail than the US. And this seems to be something where an academic consortium group could help play a role in making, both providing tools and also making a case and providing like use cases where this data would be really useful and use cases that are provided.
And do you think that's grid load or it's data center load or both? If there was a load profile data repository.
I don't want to put. Maybe I'll let Hendrik answer that.
I personally think it should be both.
Both. Nothing. Yeah. And some of this data may not be that sensitive. It's just there's a lot of guardrails around this kind of data, just in case, kind of thing. Like more being proactive, because like if something bad were to happen, then it would be a really bad kind of thing. So rather than actual concerns about the data, so some of this may not be that hard to break, whereas others could be very business sensitive. So as you get closer to user data and things like that, then typically there are more barriers. Yeah.
On the load profile data, I wonder if they're relatively easier company to deal with might be Anthropic, and that they've started to release more of their sort of economic reports about here's some profiles of users. Like it doesn't seem like that big of a jump from the things that I've seen them to report for them to say what those load profile, what a hypothetical load profile if they actually serve the use of a single data center, because they have this sort of this mix between retail / individual users and enterprise. I also know but,
So by the way, I mean, people in this room have open source things before. So one approach would be, you build it and they come. And then the other approach would be, going after some partners before building anything, with the kind of precaution that you might build it and nobody puts data in it, and it's just a nice repository with nothing in it. So any thoughts on how to make this happen? So for instance, if there was to, let's build a repository and this is for data center load data or generally grid load data, where do we see opportunities for making progress faster? And what do they get out of it? Is it just personal relationships and we convince them this is an important problem and they put their data in? Or do they get something out of it? So, for instance, maybe, not to put you on the spot, Hendrik, but you've been working in the grid space with the lack of data problem for a while. What do you think?
I mean, the one thing I would look at is at least, for what you're describing, right? You want to share data across different stakeholders. And Linux Foundation for Energy is a place to start, right? Because I already have a community. They already have 30 member companies. You bring a new project, saying, I want to do this, I want to start, load, whatever it is, good. Yeah, keep going, right?
Thank you.
It's one option.
Thank you. Any other last questions? Yes, go ahead.
Is there a way to do something to have the state mandate, make rules around entity sharing information for a certain societal benefit? Or, I guess combining this point and these points just because it's almost voluntary right now that we're talking as, you're getting something from being part of, but is there anything we can show a CISE like Massachusetts? They have a big tax incentive over data centers, but they have little leverage to make sure it works. So could they put some rules attached to it for the data centers to help the data centers help themselves before they even run it themselves?
So perhaps if there was a flexibility program that enables early interconnection, that could also require some, maybe not fine granularity, but some amount of data sharing. Is that the kind of thing?
But the early connection piece, to reflect on the DER piece we talked about earlier, and Mass is the second highest per mile connected in the US, but there was no flex and manage of the DER. So it was build and connect. So I would think the state will likely treat this the same. I'm thinking more towards just when they're in operation, how do you reduce the cost of operation?
I see. Yeah. All right. Any last minute thoughts? Go ahead. Yeah.
We do have a model lightning or revenue program for legal greenhouse gas reduction, just in terms of multi-state collaboration. Voluntary, it's carbon pricing, there's 15 different states involved. So I wonder if there can be those maybe business templates for multi-state collaboration.
That's an interesting idea too, because this space is very fragmented in the US. It doesn't necessarily have to be. There could be a lot more knowledge transfer between different states, different ISOs, different utilities, right? So interesting. So maybe looking at across states and how to apply best practices could be a way to approach this.
And this goes beyond one RTO, this particular team, so.
All right, so we'll be around for a little while longer to connect, to exchange contact information. If you have any questions, any follow-ups, feel free to reach out to one of us, me, Ajay, Adam, or to Catherine, who has been emailing you a lot to remind you about the event. Any follow-ups, please let us know. Thank you so much for coming. Some people came from out of the city, some people came from out of state. Thanks so much. And we'll be in touch. Hopefully, we'll take this into some next steps in building some new collaborations.